Good evening and welcome to The Sleepy Scientist. It's wonderful to have you here. Tonight we'll be looking at something that begins in warm sunlit water and ends kilometres below in complete darkness, under crushing pressure, in a place we've mapped less thoroughly than the surface of Mars, the deep ocean. Before we begin, a quick word about our ebook over on the Sleepy Scientist website. The QR code is up on screen, and there's a link in the description to thesleepyscientist.com. If you choose to buy it, you're the reason these videos keep appearing, and I don't think you quite understand how much that means. Thank you sincerely. Now, I'd love to know where in the world you're watching from tonight. Perhaps you're listening beneath the covers, watching the lights pass by from a late-night train, or settling into your favourite chair after a long day. Wherever you are, I hope you feel warm, comfortable, and ready to leave the noise of the surface behind for a little while. And if these slow and peaceful journeys through science help you relax, a like and a subscribe are always appreciated. Tonight we're travelling down through the ocean, leaving the sunlight behind as we pass coral reefs, clouds of plankton, lanternfish, glowing creatures, hydrothermal vents, and the vast, silent plains of the deep sea floor. I'll do my best not to make the journey so fascinating that you stay awake all night wondering what might be moving around several kilometres beneath the waves. Although should that happen, at least you'll know the anglerfish is probably having a far stranger evening than you are. So get comfortable, let the surface world fade away, and let's begin with the question waiting for us in the dark. What is down there on the long journey to the bottom of the ocean? From the surface, the ocean can appear almost simple. A broad sheet of water meets the sky at a clean horizon, disturbed only by waves, passing birds, and the occasional dark shape of land. Yet beneath that apparently flat boundary lies the largest continuous living space on Earth. The ocean covers roughly 71% of the planet's surface. It occupies most of the world we live on, even though human life is concentrated on the smaller areas of exposed land. Seen from space, Earth is not mainly a world of continents surrounded by water. It is a water-covered planet interrupted by continents. Almost all of Earth's liquid water is held within the ocean. Rivers, lakes, groundwater, clouds, ice, and the water contained inside living organisms represent only a small remainder by comparison. The ocean is therefore not simply one feature among many on the planet. It is one of the main physical systems shaping Earth's climate, chemistry, geology, and life. We usually divide it into 5 named oceans: the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, the Southern Ocean, and the Arctic Ocean. These names are useful for geography, navigation, and scientific study, but the boundaries between them are not walls. Water moves continuously between them through currents, deep circulation, tides, and the slow mixing of enormous water masses. In a physical sense, there is one global ocean. Its true scale is difficult to appreciate from the shore. The surface gives almost no indication of how much space exists underneath it. The average depth of the global ocean is approximately 3,682 metres. That means the typical seafloor lies nearly 4 kilometres beneath the surface. At that depth, several of the tallest structures ever built could be stacked one above another and still fail to reach the air. The Burj Khalifa, the tallest completed building in the world, rises a little over 800 metres. 4 of them placed vertically would still not quite reach the average ocean depth. Recreational scuba divers normally remain within the upper few tens of metres. Even highly trained technical divers operate in a very small portion of the ocean's full vertical range. The ordinary seabed is not waiting just below the world of swimmers and coral reefs. Across much of the planet it lies kilometres farther down. An average depth is only the beginning. The deepest known region is Challenger Deep, within the Mariana Trench in the western Pacific Ocean. Its floor lies close to 11 kilometres below sea level. If Mount Everest were placed at the bottom, its summit would remain submerged beneath more than 2 kilometres of water. That comparison is often used because it gives the depth a familiar shape. Even the highest mountain on Earth would disappear completely inside the deepest trench, with a substantial layer of ocean still above it. Between the surface and the bottom is the water column, the immense body of water through which sunlight, heat, oxygen, nutrients, particles, animals and chemical signals move. Scientists often refer to open water habitats as the pelagic environment. The word describes the ocean away from the coast and seafloor, including the vast spaces where fish, squid, jellyfish, plankton, and countless smaller organisms live suspended in the water. The benthic environment refers to habitats associated with the bottom. This includes soft sediment, rocky slopes, coral structures, volcanic ridges, abyssal plains, hydrothermal vents, and the steep walls and floors of trenches. The pelagic and benthic worlds are closely connected. Material produced near the surface sinks toward the bottom. Animals migrate upward and downward. Currents carry dissolved chemicals across great distances. The seafloor releases heat and minerals into the water, while the remains of surface life gradually settle onto the seabed. To make sense of this enormous vertical world, oceanographers divide it into broad depth regions. The uppermost is the sunlit zone, where enough light penetrates for photosynthesis. Beneath it is the twilight zone, where sunlight becomes faint and blue, but has not yet vanished completely. Deeper still is the midnight zone, a region of permanent natural darkness. Below that lies the abyssal zone, extending through the cold water above much of the deep sea floor. Finally, within the deepest trenches, the ocean enters the Hadal zone, named after Hades, the underworld of ancient Greek mythology. The precise boundaries between these regions can vary slightly depending on the scientific classification being used. Nature rarely places neat signs at the agreed depths. Light fades gradually. Temperature changes unevenly. Oxygen levels differ between regions. Trenches begin at different depths. Even so, these zones describe real environmental transitions. As depth increases, light weakens and then disappears. Colours vanish one by one. Temperature generally falls. Pressure rises steadily under the weight of the water above. Food becomes less abundant and less predictable. Oxygen may decrease in some layers and increase again in deeper water carried from colder regions. Life must change with these conditions. Bodies become transparent, silver, black, red, soft, expandable or gelatinous. Eyes may grow enormous, shrink or disappear. Some animals produce their own light. Others rely on vibration, smell, touch, pressure changes or chemical traces. Movement becomes economical because every unnecessary burst of energy has a cost. Far below the influence of sunlight, ecosystems can even be supported by chemical energy released from the seafloor. Measurements gathered and communicated by organizations such as the National Oceanic and Atmospheric Administration, the United States Geological Survey, and Woods Hole Oceanographic Institution have helped reveal the scale of this hidden world. Yet much of it remains only broadly mapped, briefly visited, or entirely unobserved. The descent begins in familiar blue water, but familiarity will not last for long. With every meter, the surface becomes more distant, sunlight becomes weaker, and the ocean changes from a bright extension of the world above into an environment ruled increasingly by darkness, pressure, chemistry, and the slow movements of the Earth itself. The ocean's size presents an immediate problem. How can anyone measure the shape of a world hidden beneath kilometers of sea water, when a person at the surface can see only a short distance below? Sunlight is quickly absorbed and scattered. Cameras become useful only when carried into the depths with their own lights, and even then they reveal little more than the water directly around them. To understand the wider landscape, oceanographers have had to learn how to map without seeing. The measurement and mapping of underwater depth is called bathymetry. A bathymetric map is the submerged equivalent of a topographic map on land. Instead of showing elevations above sea level, it shows depths below it. Contour lines and changes in colour reveal mountains, valleys, ridges, plains, canyons, and steep escarpments concealed beneath the ocean surface. For most of human history, the simplest method was to lower a weighted line over the side of a vessel. When the weight reached the bottom, the length of line released provided an estimate of depth. Some sounding devices also collected a small sample of sediment, offering a clue as to whether the seabed consisted of sand, mud, shells, or rock. The method was slow and uncertain. Currents could pull the line sideways, while several kilometres of rope might be lowered and recovered for a single measurement. It was careful science, although not especially generous to anyone hoping for quick results. Between 1872 and 1876, the British research vessel Challenger carried out the first great global oceanographic expedition under the scientific direction of Charles Wyville Thomson. The naturalist John Murray became one of its most important researchers and later supervised the publication of much of its vast scientific record. The expedition measured depths, collected water and sediment, recorded temperatures, and recovered organisms from places once assumed to be lifeless. Its isolated soundings could not produce a continuous map, but they showed that the seabed was deep, varied, and biologically inhabited. A much faster method arrived through the use of sound. An echo sounder sends a sound pulse downward from a ship. The pulse travels through the water, reflects from the seabed, and returns as an echo. By measuring the total travel time and accounting for the speed of sound in seawater, researchers can calculate the distance to the bottom. Early systems measured a narrow line beneath the vessel. Modern multi-beam sonar sends out many sound beams at once in a broad fan shape. As a ship moves forward, the system surveys a wide strip of seabed. These overlapping strips can be combined into a detailed three-dimensional representation of underwater terrain. Multi-beam sonar can reveal volcanic cones, landslides, channels, fracture zones, and ridges. It can also record backscatter, providing clues about whether the bottom is smooth, rough, soft, or hard. Ships cannot survey every ocean basin quickly, so satellites provide a broader but less detailed view. Large underwater mountains and trenches slightly alter Earth's gravitational field. A seamount contains additional mass, producing a tiny outward bulge in the sea surface above it. Deep depressions can create the opposite effect. Satellite radar altimeters measure these subtle changes in sea surface height. Scientists combine them with gravity calculations and direct ship measurements to infer the broad shape of the seabed. These maps are useful, but they are estimates rather than close surveys. They may reveal a major ridge while missing smaller features that multi-beam sonar can resolve. The value of detailed mapping became especially clear through the work of geologist Marie Tharp and geologist Bruce Heason. During the middle of the 20th century, Tharp transformed long lines of shipboard depth measurements into carefully drawn profiles of the Atlantic seafloor. She identified a deep rift valley running along the centre of the mid-Atlantic ridge. As information from other oceans accumulated, Tharp and Heason helped reveal that the mid-ocean ridges form a connected global mountain system. Their maps provided powerful evidence for seafloor spreading and helped strengthen the theory of plate tectonics, in which Earth's outer shell is divided into moving plates. Yet mapping is not the same as exploring. A sonar survey may establish that a canyon exists without photographing its walls. A satellite may suggest a mountain that has never been visited. A mapped plain may never have been sampled for sediment, microorganisms, or animals. Direct exploration therefore uses complementary tools. Crude submersibles carry people into the deep. Remotely operated vehicles remain connected to a ship, while autonomous underwater vehicles follow programmed routes without a physical connection. Deep-sea landers record images, chemistry, currents, or animal activity. Sediment corers recover layered material from the seabed. Sonar reveals broad terrain, while cameras inspect small areas in greater detail. Each tool answers a different part of the question. In April 2026, the General Bathymetric Chart of the Oceans reported that approximately 28.7% of the global seafloor had been mapped to modern standards. That represented roughly 104 million square kilometres, yet well over two-thirds still lacked comparable direct coverage. The General Bathymetric Chart of the Oceans and the Nippon Foundation. General Bathymetric Chart of the Oceans, Seabed 2030. Project are gathering measurements from governments, research institutions, commercial vessels and scientific expeditions to build an increasingly complete global map. The remaining gaps are not simply blank spaces waiting to be coloured. They may contain unrecorded seamounts, canyons, fault systems, habitats, and species. The ocean floor is understood well enough to reveal its immense structure, yet incompletely enough that every descent passes through a mixture of established science and genuine uncertainty. Beneath the smooth horizon is a landscape humanity has measured in fragments, inferred through gravity, traced with sound, and visited one small patch at a time. At the precise boundary where the ocean meets the air, two enormous worlds remain in constant contact. The surface may look like a simple dividing line, but it is not a lid resting quietly over the water below. It is a restless interface through which heat, gases, fresh water, energy, particles, and living organisms are continually exchanged. Sunlight passes downward into the upper ocean. Heat moves both into and out of the water. Rain adds fresh water, while evaporation removes it and leaves dissolved salts behind. Oxygen and carbon dioxide cross between the atmosphere and the sea. Dust, pollen, volcanic ash, microorganisms, and human-made material settle onto the water, while droplets and sea salt are thrown back into the air. Even on a calm day, the surface is busy. Most visible waves begin with wind. As air moves across the ocean, friction transfers some of its energy into the water. Small ripples form first. These give the wind a rougher surface to grip, allowing larger waves to develop as more energy is added. A passing wave gives the impression that a large body of water is travelling steadily forward. In reality, the individual water particles usually move in looping or nearly circular paths. They rise, move forward, sink, and move backward as the wave passes. Energy travels across the surface far more efficiently than the water itself. This is why a floating object may bob up and down as waves move beneath it without being carried forward at the same speed as the wave crests. There is some net movement, especially in breaking waves and near the shore. But the visible travelling shape is not simply a parcel of water rushing intact across the ocean. Wind also helps drive surface currents. Persistent winds push the upper layers of the sea, contributing to the large rotating current systems known as ocean gyres. Yet the water does not move in exactly the same direction as the air above it. Earth is rotating beneath the ocean, and this produces the Coriolis effect. Moving water is deflected to the right of its path in the northern hemisphere and to the left in the southern hemisphere. The effect is negligible over very short distances, but across an ocean basin it becomes central to the pattern of circulation. The Swedish oceanographer Vagan Walfrid Ekman developed an explanation for how wind and Earth's rotation influence the upper ocean. In what is now called the Ekman spiral, each layer of moving water drags the layer beneath it, while the Coriolis effect turns each successive layer slightly farther from the wind direction. When the movement of these layers is considered together, the average transport of water occurs roughly at a right angle to the wind. This is called Ekman transport. It helps create coastal upwelling, where surface water is moved away and colder. Nutrient-rich water rises from below to replace it. The surface also receives the greatest share of the sun's energy, but that heating is uneven. Tropical waters receive more direct sunlight than polar waters. Summer surfaces warm more strongly than winter surfaces. Clouds, winds, currents, and the length of the day all influence how much energy is absorbed. Warm water is generally less dense than cold water. Fresh water is also less dense than salty water. Differences in temperature and salinity therefore create differences in density, helping to organise the ocean into layers and contributing to currents at both local and planetary scales. These temperature contrasts also affect the atmosphere. Warm ocean surfaces can transfer heat and moisture into the air, helping to power weather systems. Cooler surfaces may absorb heat instead. The ocean stores and moves immense amounts of energy, softening some temperature changes while strengthening others. At the boundary itself, gases are constantly exchanged. Oxygen from the atmosphere dissolves into seawater, particularly when the water is cool and disturbed by waves. Oxygen produced by photosynthetic organisms can also enter the atmosphere or remain dissolved for marine life to use. Carbon dioxide moves in both directions. The ocean absorbs large quantities from the atmosphere, but it can also release carbon dioxide where water becomes warmer, where currents bring carbon-rich deep water upward, or where biological and chemical conditions favour its escape. Temperature matters because cold water can generally hold more dissolved gas than warm water. Waves and turbulence matter because they continually renew the boundary between air and water. Living organisms matter because photosynthesis removes carbon dioxide and produces oxygen, while respiration and decomposition consume oxygen and release carbon dioxide. Wind and waves also stir the upper ocean. This mixing can create a surface layer in which temperature, salinity, and other properties remain relatively uniform over tens of meters. Beneath it, the temperature may begin to fall much more rapidly. This transitional region is called the thermocline. In some places, it persists through much of the year. Elsewhere, storms and seasonal cooling can weaken it by mixing the water more deeply. The thermocline is more than a change in temperature. It can slow the exchange of nutrients, oxygen, and heat between surface water and the deeper ocean. It helps separate the bright weather-influenced upper layer from the colder and more stable environment below. Pressure is also beginning to change, although gently at first. Every metre of descent places another metre of seawater overhead. The weight of that water increases hydrostatic pressure steadily with depth. Near the surface, the difference is modest. Farther down, it becomes one of the defining physical challenges of the ocean. For now, it is simply an invisible reminder that the water above is accumulating. At the surface, sunlight is strong, temperatures are comparatively warm, gases move freely, and weather can rearrange the water within hours. Waves rise and collapse, rain falls, winds strengthen and fade. The atmosphere and ocean remain closely connected. This bright and restless skin provides the reference point for everything beneath it. As the descent continues, motion will become less visible, sunlight will weaken, warmth will diminish, and the atmosphere will gradually lose its immediate influence. The surface is not the ocean's quiet roof. It is its busiest doorway. Sunlight does not reach very far into the ocean, but within the uppermost layer it transforms the water completely. This bright region is known as the epipelagic zone, or more simply, the sunlit zone. It begins at the surface and usually extends down to around 200 meters in clear, open water. That boundary is only approximate. The true depth of useful light changes from place to place and from season to season. Cloud cover can reduce the amount of sunlight entering the sea. At high latitudes, the sun may sit lower in the sky. Suspended sediment can make coastal water murky, while large concentrations of plankton can absorb and scatter light near the surface. In very clear tropical water, faint light may travel surprisingly deep. In a muddy estuary, useful light may disappear after only a few meters. Despite occupying only a small fraction of the ocean's total volume, the sunlit zone is where most marine food webs begin. It contains enough light for photosynthesis, the process by which certain organisms capture light energy and convert it into chemical energy stored within organic matter. During photosynthesis, Carbon dioxide and water are used to build energy-rich molecules. Oxygen is released as a byproduct. The precise chemistry is complex, but the high-level principle is simple. Sunlight is taken from the environment and stored in a form that living organisms can use. On land, this work is performed mainly by plants. In the open ocean, it is carried out largely by phytoplankton. Phytoplankton are drifting photosynthetic organisms, but they are not one single biological group. The name describes a way of life rather than a close family relationship. Some are bacteria, others are single-celled organisms with intricate shells, flagella or mineral plates. Diatoms build delicate outer walls from silica, the same basic material found in glass. Dinoflagellates often move using two whip-like structures and include both harmless species and some capable of producing powerful toxins. Cyanobacteria are photosynthetic bacteria with an ancient evolutionary history. Coccolithophores surround themselves with tiny calcium carbonate plates that can accumulate in immense numbers. Individually, most phytoplankton are microscopic. Collectively, they influence the chemistry, colour, climate and biology of the entire planet. They form the first major step in many oceanic food chains. Tiny grazers consume them. Small fish feed on those grazers. Larger fish, seabirds, squid, sharks, dolphins and whales feed at progressively higher levels. The animals drifting with the currents are known as zooplankton. Some remain planktonic throughout their lives, including copepods, krill, and many jelly-like organisms. Others are plankton only temporarily. The larvae of crabs, sea stars, mollusks, worms, and fish may spend their early lives floating through the sunlit water before settling onto the seabed or developing into stronger swimmers. This means a small container of seawater can hold the early stages of animals that will eventually look entirely different. Life near the surface is rich in energy, but sunlight alone is not enough. Phytoplankton also require nutrients, including nitrate and phosphate. Diatoms additionally need silicate to construct their glass-like walls. These nutrients are not distributed evenly. In many regions, they become trapped beneath the upper layer of warm water. Sunlight heats the surface, making the water warmer and usually less dense. Below it lies colder, denser water. When the difference is strong enough, the ocean becomes stratified, meaning it is arranged into layers that resist mixing. The warm upper layer receives abundant sunlight, but may gradually lose its nutrients as phytoplankton use them. Deeper water may contain plenty of nutrients released by decomposition, but it receives too little light for photosynthesis. The most productive regions are often those where this separation is disturbed. Upwelling occurs when deeper water rises toward the surface. Winds can push surface water away from a coastline or cause waters to diverge in the open ocean. Cold, nutrient-rich water then moves upward to replace it. This rising water carries nitrate, phosphate, silicate, and other dissolved materials into the illuminated zone. Phytoplankton respond rapidly, creating blooms that can support enormous populations of fish, seabirds, and marine mammals. Some of the world's most productive fisheries are found in major upwelling regions, including waters off Peru, California, Northwest Africa, and Southwestern Africa. The contrast between light and nutrients explains why clear tropical seas can sometimes appear almost empty. Their brilliant blue colour often indicates that there are relatively few suspended particles and low concentrations of phytoplankton. Sunlight is plentiful, but nutrients may be scarce. Colder waters can look greener or cloudier because they contain more phytoplankton. In temperate and polar regions, winter storms may mix nutrients upward. When spring brings longer days and stronger sunlight, phytoplankton can multiply dramatically. The result is a seasonal bloom, a vast but temporary expansion of microscopic life. The open sunlit ocean is different from shallow coastal water, where light may reach the seabed. In these places, larger photosynthetic organisms can grow directly from the bottom. Seagrasses form meadows in sheltered coastal environments. Kelp forests rise through cold, nutrient-rich water. Reef-building corals thrive in warm, clear, shallow seas, supported partly by photosynthetic organisms living inside their tissues. These coastal habitats are visually dramatic, but the open ocean is powered largely by organisms too small to see without magnification. The energy captured here does not remain near the surface. Some phytoplankton are eaten immediately, some die and sink. Zooplankton produce waste that falls downward. Mucus, shells, fragments of tissue, and other organic particles drift into darker water below. This falling material will eventually become part of the food supply for animals living hundreds or thousands of meters beneath the sunlight. Even deep-sea predators that have never seen the surface often depend on energy first captured here. Their prey may eat smaller animals, which fed on drifting particles, which began as living cells built with sunlight. The connection can become long, indirect, and almost impossible to recognize, but it remains. The sunlit zone is therefore more than the bright entrance to the ocean. It is the energetic foundation supporting most of the life below, a thin, illuminated layer carrying the weight of an entire dark world. Coral reefs are among the most intricate structures found anywhere in the ocean. From a distance, they can resemble underwater gardens or brightly coloured rock formations, but neither description is quite accurate. A coral reef is a living construction, assembled slowly by countless small animals across many generations. Reef-building corals belong to the phylum Cnidaria, the same broad animal group that includes jellyfish and sea anemones. A coral colony is made up of many individual animals called polyps. Each polyp has a soft cylindrical body, a central mouth, and a ring of tentacles used to capture food from the surrounding water. The polyps are usually only a few millimeters or centimeters across, yet together they can build structures stretching for hundreds or even thousands of kilometers. Most reef-building corals produce hard skeletons made from calcium carbonate. As one generation grows over the remains of earlier generations, these skeletons accumulate into a solid framework. Living coral usually occupies only a thin outer layer, while much of the reef beneath it consists of material produced by animals that died long ago. The resulting structure is shaped not only by coral growth, but also by waves, currents, erosion, storms, grazing animals, boring organisms, and the gradual cementing of the loose fragments. A reef is therefore both alive and geological, built by biology, but altered constantly by the physical ocean. Much of the energy supporting tropical reef-building corals comes from microscopic photosynthetic organisms living inside their tissues. These organisms belong mainly to the family Symbodiniaceae and are often known as zooxanthellae. The relationship is a form of symbiosis, meaning that two different organisms live closely together in a way that benefits both. The symbiotic algae receive shelter, carbon dioxide, and access to waste nutrients released by the coral. In return, they use sunlight to produce energy-rich compounds through photosynthesis, supplying a large share of the coral's energy needs. This partnership explains why most tropical coral reefs occur in shallow, clear water. The symbiotic organisms require enough light to photosynthesize, so reef-building corals must remain within the illuminated part of the ocean. Sediment-rich or murky water reduces the available light, while excessive sediment can also settle on the coral surface and interfere with feeding and respiration. The clearest tropical seas may look almost empty from above, yet close to the coast they can support extraordinary reef communities. Warm temperatures, clear water, suitable depth, stable salinity, and a solid surface for attachment create the conditions in which coral colonies can gradually expand. The distribution of coral reefs also reveals how the seafloor itself changes over time. During the voyage of HMS Beagle, Charles Darwin considered why coral reefs appeared in several distinct forms. Some reefs cling closely to the shores of islands and are known as fringing reefs. Others lie farther offshore, separated from land by a lagoon, and are called barrier reefs. Atolls form rings around central lagoons, sometimes with no high island remaining above the water. Darwin proposed that these forms could represent stages of one long geological process. Coral would first grow around a volcanic island. As the island slowly subsided or the seafloor beneath it sank, the coral would continue growing upward towards sunlight. The island would gradually become lower, while the reef remained near sea level. A fringing reef could therefore become a barrier reef, and eventually an atoll, as the original volcanic island disappeared beneath the surface. Later evidence from drilling and modern geology strongly supported this explanation. Once established, the physical structure of a reef creates an extraordinary variety of habitats. Crevices provide shelter from predators, overhangs create shaded spaces, branching corals form nurseries for small fish. Flat surfaces support algae, sponges, and encrusting organisms. Fish use reefs as feeding grounds, resting places, territories, and hunting areas. Crustaceans hide inside cracks. Mollusks graze, filter water, or burrow into the structure. Worms build tubes or bore into old skeletons. Sponges filter particles from the water. Microorganisms live across the coral surface, inside sediments, and within the reef framework itself. A healthy reef is therefore less like a single organism and more like a densely occupied city, although one with considerably more mucus and far fewer planning regulations. This complexity also makes reefs vulnerable to changes in their environment. Coral bleaching occurs when stress disrupts the relationship between the coral and its symbiotic algae. Prolonged heat is one of the most common causes. Under stressful conditions, the algae may be expelled or lose their pigments, leaving the pale coral skeleton visible through the animal's transparent tissue. A bleached coral is not necessarily dead. The polyps may remain alive for a time, and can sometimes regain their symbiotic partners if conditions improve. However, bleaching removes an important source of energy. If stressful temperatures continue, the coral may starve, become more vulnerable to disease, reproduce less successfully, or die. Another long-term pressure comes from ocean acidification. The name can sound as though the ocean is becoming strongly acidic, but seawater remains mildly alkaline. The change refers to a reduction in its acidity level, as the ocean absorbs additional carbon dioxide from the atmosphere. When carbon dioxide dissolves in seawater, it alters the balance of dissolved carbon compounds and reduces the availability of carbonate ions. Corals use these ions to build calcium carbonate skeletons. If carbonate becomes less available, construction can require more energy, and existing reef material may become easier to erode. Rising temperature, acidification, pollution, sediment, overfishing, disease, and destructive storms can interact, making it difficult for damaged reefs to recover. Scientific organizations monitor these changes over large areas. The National Oceanic and Atmospheric Administration Coral Reef Conservation Program supports research, management, restoration, and protection. Coral Reef Watch uses satellite data and ocean observations to track sea surface temperatures and estimate where corals may be experiencing dangerous heat stress. The vivid fish and branching corals make reefs appear to be the most important life in the water, but much of their energy begins at a far smaller scale. Inside coral tissue floating through the surrounding sea and forming the foundation of wider marine food webs are photosynthetic organisms too small to notice individually. Their combined activity supports not only coral cities in shallow water, but much of the living ocean beyond them. The most important organisms in the sunlit ocean are often among the easiest to overlook. They do not form towering reefs, breach the surface, or move in glittering schools. Most are too small to see without a microscope. Yet these drifting cells help support marine food webs, influence the atmosphere, and move carbon through the ocean on a planetary scale. They are known collectively as phytoplankton. The name combines words meaning plant and wanderer. Although phytoplankton are not all plants in the strict biological sense, they include organisms from several very different branches of life. What unites them is their ability to photosynthesize while drifting through illuminated water. Some phytoplankton can swim weakly using tiny structures, but most cannot move strongly enough to overcome large currents. They travel with the water around them, rising, sinking, dividing, and being eaten as the upper ocean shifts. Among the most familiar groups are diatoms. These single-celled organisms build protective outer walls from silica, the same basic substance found in glass. Their shells, known as frustules, often consist of two fitted halves, covered with delicate pores and geometric patterns. Diatoms are especially abundant in nutrient-rich coastal waters, upwelling regions, and high-latitude seas. They require dissolved silicate to build their shells, linking their growth to the supply of minerals carried upward from deeper water. Coccolithophores take a different approach. They surround themselves with tiny overlapping plates of calcium carbonate called coccoliths. When enormous numbers of these organisms gather near the surface, the plates can scatter light strongly enough for the bloom to be visible from space. Dinoflagellates are another varied group. Many have two whip-like flagella that allow them to move through the water. Some photosynthesize, some consume other organisms, and some combine both strategies. Certain dinoflagellates produce toxins capable of accumulating in shellfish or harming fish, marine mammals, and people. Others generate bioluminescence, causing disturbed water to flash blue at night. A quiet shoreline can therefore become briefly luminous simply because millions of microscopic cells have been jostled by a wave. The cyanobacteria Prochlorococcus and Synechococcus are far smaller than most diatoms and dinoflagellates. Prochlorococcus is among the smallest known photosynthetic organisms and is especially abundant in warm, nutrient-poor regions of the open ocean. Its individual contribution is tiny. Its global contribution is not. Across vast areas of tropical and subtropical water, enormous populations of these cells continually capture sunlight and carbon dioxide. Photosynthesis depends on pigments that absorb light. Chlorophyll is the best known, particularly chlorophyll A, which is used by oxygen-producing photosynthetic organisms. Additional pigments capture wavelengths that chlorophyll absorbs less efficiently and pass that energy into the photosynthetic system. These accessory pigments help different phytoplankton groups live under different light conditions. They also influence ocean colour, giving researchers indirect clues about the organisms present near the surface. During photosynthesis, phytoplankton use light energy to turn carbon dioxide and water into organic matter. Oxygen is released in the process. Marine photosynthetic organisms are estimated to produce roughly half of the oxygen generated on Earth each year. That fact is often shortened into the memorable claim that every second breath comes from the ocean. It is a useful way to express the scale of marine photosynthesis, but it can also create the wrong impression. The oxygen released by present-day phytoplankton does not simply accumulate untouched in the atmosphere for humans to breathe. Marine organisms also consume oxygen through respiration. Bacteria and other decomposers use it while breaking down dead material. Much of the oxygen produced within the ocean is therefore used again within the ocean. The atmosphere contains an enormous reservoir of oxygen, accumulated over geological time. Its present concentration reflects a long balance between photosynthesis, respiration, burial, oxidation, and other processes operating across both land and sea. So the ocean contributes enormously to annual oxygen production, but this is not the same as saying that half of every breath consists of oxygen freshly released by plankton earlier that morning. The organic matter built by phytoplankton supports the wider food web. Copepods and other zooplankton graze upon them. Small fish feed on the zooplankton. Larger fish, squid, seabirds, seals, and whales consume those animals in turn. Even the largest creatures may depend on microscopic producers. Blue whales feed largely on krill, which consume phytoplankton directly, or feed within plankton-based food webs. The connection between a whale and a single photosynthetic cell may involve only a few feeding steps. Phytoplankton populations can change rapidly when conditions become favourable. A sudden increase is known as a bloom. Light is essential, but it is only one part of the equation. Nutrients such as nitrate, phosphate, iron, and silicate can limit growth. Temperature affects metabolism. Mixing determines whether cells remain near the light or are carried into darkness. Grazing by zooplankton can remove phytoplankton almost as quickly as they reproduce. In temperate and polar waters, winter mixing may bring nutrients upward while short days restrict growth. When spring arrives, increasing sunlight can allow phytoplankton to multiply before grazers catch up. This creates the spring bloom, one of the largest recurring biological events in the ocean. Not all of the carbon captured during a bloom remains near the surface. Some cells die. Some are only partly eaten. Zooplankton produce dense fecal pellets. Gelatinous organisms discard feeding structures made from mucus. Shells, fragments, aggregates, and pieces of tissue begin to fall. This downward movement forms part of the biological carbon pump. Carbon dioxide absorbed near the surface becomes incorporated into living matter. A fraction of that matter then sinks through the water column. Some is consumed and returned to the water as carbon dioxide at shallow depth. Some travels much farther before being decomposed. A very small portion may eventually reach the seabed and become buried in sediment. The process is not a single pump in the mechanical sense. It is the combined result of countless organisms feeding, growing, producing waste, dying, and sinking. Yet together these activities move carbon away from the atmosphere and upper ocean, sometimes storing it at depth for decades, centuries, or longer. Scientists observe phytoplankton over immense areas using satellites. Instruments measure light reflected from the ocean and detect subtle differences in colour. Researchers can then estimate quantities such as chlorophyll concentration and identify the broad outlines of blooms. Satellite measurements provide coverage that ships alone could never achieve, but colour does not reveal everything. Similar signals can be produced by different organisms, sediments, or dissolved materials. Clouds block the view, and satellites mainly observe the surface layer. Ships collect water samples for microscopes, genetic analysis, chemical measurements, and pigment studies. Floats and gliders travel through the water carrying sensors for light, oxygen, temperature, salinity, and particles. Each approach adds detail that colour alone cannot provide. The National Aeronautics and Space Administration Plankton, Aerosol, Cloud, Ocean Ecosystem Mission was developed to improve this global view. Its instruments study ocean colour in greater detail while also observing atmospheric particles and clouds. This allows researchers to examine connections between phytoplankton, aerosols, carbon cycling, climate, and the movement of matter between ocean and atmosphere. Near the surface, phytoplankton capture sunlight and briefly turn it into living tissue. Below them, small particles begin a slow descent through darker water. Much will be eaten before travelling far. Some will be broken apart, repackaged, or dissolved. A small amount will continue downward for hundreds or thousands of meters. For the deep ocean, this gentle rain of organic material will become one of the most important links to the bright world above. As the descent continues, the ocean does not simply become darker, it changes colour. Near the surface, sunlight appears almost white because it contains many different wavelengths of visible light. Human eyes interpret those wavelengths as the familiar spectrum running from red through orange, yellow, green, blue, and violet. Once sunlight enters seawater, however, those colours do not travel equally far. Water absorbs some wavelengths more readily than others. The longer wavelengths associated with red light are generally removed first. Orange fades next, followed by much of the yellow. Shorter blue and blue-green wavelengths can travel farther through clear seawater before they too are absorbed or scattered away. This selective loss of colour is one reason the open ocean appears blue. It is not simply reflecting the sky, although reflection can contribute at the surface. Water itself interacts with light in a way that favours the survival and return of blue wavelengths. Within the first few metres, the strongest reds begin to weaken. By somewhere around 10 metres, depending on conditions, red objects can appear noticeably darker. As the descent continues, orange and yellow become less distinct. Green and blue remain visible for longer until eventually even they fade into darkness. These depths are not fixed boundaries. Light behaves differently in different bodies of water. Clear tropical ocean water may allow blue light to penetrate to considerable depths. Coastal water often contains suspended sediment, microscopic organisms, and dissolved organic material that absorb and scatter light more strongly. A river entering the sea may carry fine particles that turn the water brown or green. A dense plankton bloom can reduce visibility close to the surface. The angle of the sun, the season, cloud cover, waves, and the time of day all alter the amount of light available below. In very clear open water, blue is usually the colour that reaches deepest. In coastal or sediment-rich environments, green light may travel more effectively because blue wavelengths are scattered or absorbed by the material in the water. The result is not one universal sequence occurring at exactly the same depth everywhere. It is a gradual filtering process shaped by the character of the water itself. Colour also depends on illumination. A red object appears red because it reflects red wavelengths toward the eye while absorbing much of the remaining visible light. If no red light reaches it, there is very little red light available to reflect. Under natural blue illumination, a red fish does not continue glowing red simply because that is its surface colour. It may appear dark grey, brown, or almost black. This creates a useful form of camouflage. Many animals living below the strongly illuminated surface are red or deep orange. To human eyes under white light they may look strikingly bright. In their natural environment, where red wavelengths are absent, the same animals can become extremely difficult to see. Black pigmentation works by absorbing much of the light that reaches the body. Some deep-sea fish are among the darkest animals known, reflecting only a tiny fraction of incoming light. This reduces the chance that flashes of bioluminescence will reveal their outlines. Other animals avoid detection by becoming almost transparent. Gelatinous bodies, clear tissues, and reduced pigmentation allow much of the available light to pass through, rather than being reflected. Transparency is not perfect. Eyes, digestive organs, and food inside the body still need to be concealed. Some animals hide these visible parts with mirrored surfaces, dark pigment, or reflective tissue. Silver is another effective colour in open water. The sides of many fish contain reflective crystals that act like tiny mirrors. Rather than displaying one obvious colour, the body reflects the surrounding light. Viewed from the side, a silverfish may blend into the diffuse brightness of the water around it. The disguise changes as the fish turns, which is useful in an environment where there is rarely a convenient rock or plant to hide behind. Light underwater is not only absorbed, it is also scattered. Scattering occurs when light is redirected by water molecules, particles, plankton, and other material. Instead of travelling in a perfectly straight line, some light is deflected in different directions. This makes underwater illumination softer and less clearly directional. Shadows become faint, edges lose contrast. Distant objects blur into the surrounding water. A beam from a diver's torch may look sharply defined because particles scatter part of its light toward the observer. Natural sunlight behaves more diffusely, especially after travelling through many meters of water. The deeper the descent, the less obvious it becomes where the light is coming from. Near the surface, the direction of the sun is clear. Farther down, the remaining light may seem like a dim blue glow spread across the water above. Submersibles and remotely operated vehicles transform this world when they switch on powerful lamps. A seemingly colourless animal may suddenly appear scarlet. Orange coral, yellow sponges and pink crustaceans emerge from darkness with almost unnatural brightness. The lights have not created those colours, they have restored the missing wavelengths. White lamps contain red, orange, yellow, green and blue light, allowing surfaces to reflect colours that natural sunlight can no longer deliver at that depth. When the lamps move away, the same animals return to grey, black or invisibility. This can make deep-sea footage slightly misleading. The bright colours are physically real, but the animals themselves may never normally see one another in that way. As red disappears, the surface world begins to feel more distant. Warm colours are quietly removed from the landscape. The water becomes increasingly blue, then blue-grey, and finally almost colourless. Photosynthesis depends on usable light, and eventually too little remains for it to continue. The productive brightness of the upper ocean gives way to a region where organisms can no longer rely on sunlight to build food. The loss of red is therefore more than a visual curiosity. It is an early sign that the ocean is approaching a different biological world. Colour is fading. Sunlight is weakening. And below, the last natural glow is beginning to disappear. At around 200 metres beneath the surface, the ocean enters a region where sunlight is still present, but no longer strong enough to support photosynthesis. This is the mesopelagic zone, more commonly known as the twilight zone. It usually extends from approximately 200 metres down to about 1,000 metres, although these boundaries are not perfectly fixed. The transition depends on how much light entered the ocean at the surface and how quickly the water absorbed or scattered it. In clear tropical seas, traces of sunlight may penetrate deeper. In coastal water filled with sediment, plankton, or dissolved organic material, the same level of darkness can begin much closer to the surface. There is no visible line marking the entrance. The water does not suddenly change from one zone into another. Instead, the blue light above becomes progressively weaker until it resembles a distant glow rather than ordinary daylight. Looking upward, an animal may still detect the faint brightness of the surface. Looking sideways or downward, the surrounding water may already appear almost completely dark. This makes the twilight zone a place between two worlds. Sunlight still influences behaviour, vision, and camouflage, but it can no longer provide enough energy for plants or phytoplankton to grow. Every animal living here depends directly or indirectly on food produced elsewhere. The region is far larger than it may first appear. A vertical range of around 800 metres stretches across much of the global ocean. It is not a narrow boundary layer, but an immense three-dimensional habitat containing enormous populations of fish, squid, crustaceans, gelatinous animals, and microorganisms. Many of these creatures are small, yet their combined abundance may be extraordinary. Lanternfish, bristlemouths, hatchetfish, shrimps, copepods, jellyfish, siphonophores, and squid occupy different depths within the dim water. Some drift slowly, others swim continuously. Many rise and fall through hundreds of meters each day. The physical environment changes as well. Temperature often continues to fall through the upper part of the twilight zone, particularly where the main thermocline separates warm surface water from the colder ocean below. Within the thermocline, temperature may decline rapidly over a relatively short vertical distance. A submersible descending through it can leave warm tropical water and enter much colder conditions without travelling especially far horizontally. The exact pattern depends on latitude and season. In polar regions, the surface may already be cold, so the temperature difference is less dramatic. In tropical oceans, the contrast between warm surface water and the deeper layers can be much stronger. Oxygen also varies with depth. Near the surface, oxygen enters from the atmosphere, and is produced by photosynthesis. Deeper down, there is no local photosynthesis to replace the oxygen consumed by respiration and decomposition. In some parts of the ocean, this creates an oxygen minimum zone. Organic matter sinking from above is consumed by animals and microorganisms, which use dissolved oxygen as they respire. If water circulation does not replace that oxygen quickly enough, its concentration can fall to very low levels. These zones are especially pronounced in parts of the eastern tropical Pacific Ocean, the northern Indian Ocean, and other regions where biological productivity is high and ventilation is limited. Low oxygen does not make the water entirely lifeless. Instead, it favours organisms with specialised adaptations. Some animals have pigments that bind oxygen very efficiently. Others reduce their metabolism, limit unnecessary movement, or tolerate chemical conditions that would be stressful for most surface species. Certain microbes use alternatives to oxygen in their metabolism, contributing to the cycling of nitrogen and other elements. For larger animals, the edge of an oxygen minimum zone can act as both refuge and barrier. Prey species capable of tolerating low oxygen may escape predators that cannot follow them. At the same time, their own movements become restricted to water, in which their bodies can continue functioning. Light, however faint, creates another set of challenges. An animal viewed from below may appear as a dark silhouette against the weak glow above. To reduce that outline, many twilight zone species have narrow bodies or reflective surfaces. Silver scales can mirror the surrounding water, making the body less obvious from the side. Transparent tissues allow light to pass through with less reflection. Dark pigmentation helps absorb stray light from flashes and bioluminescent signals. Many species have enlarged eyes capable of detecting extremely low levels of illumination. Some eyes point upward, allowing the animal to search for the silhouettes of prey moving above. Barrel-eye fish take this arrangement to a remarkable extreme. Their tubular eyes are enclosed within a transparent shield and can rotate to look upward or forward. The design is unusual, but in dim water, every available photon is worth treating with a certain amount of respect. Vision is only one source of information. Fish use the lateral line system to detect small changes in water movement and pressure. Long antennae allow crustaceans to sense nearby objects. Chemical receptors reveal food, predators, and possible mates long before they can be seen. Many animals also possess photophores, specialized organs that produce controlled light. These can be arranged in rows, patches, or species-specific patterns across the body. Photophores may help animals recognize one another, attract prey, confuse predators, or hide their silhouettes through counter-illumination. In a region defined by faint light, producing exactly the right amount of brightness can be more useful than simply glowing as strongly as possible. Food enters the twilight zone mainly from above. Dead phytoplankton, fragments of animals, discarded mucus, fecal pellets, shells, and other organic particles fall continuously through the water. Together, this material is known as marine snow. The name suggests something soft and peaceful, and from a distance it can look exactly that way. Yet each particle is part of an active biological process. Bacteria colonize the falling material. Zooplankton bite pieces from it. Small particles stick together into larger aggregates. Other pieces break apart, dissolve, or are repackaged into denser waste pellets that sink more rapidly. The twilight zone therefore acts as a filter between the surface and the deep ocean. Much of the carbon leaving the sunlit zone is consumed and returned to the water before it can descend farther. Some becomes carbon dioxide through respiration. Some is incorporated into new bodies. A smaller fraction continues downward into the midnight and abyssal zones. Understanding how much material passes through this filter is important for climate science, because it affects how long carbon remains separated from the atmosphere. Woods Hole. Oceanographic Institution's Ocean Twilight Zone project studies these processes using acoustic instruments, autonomous underwater vehicles, imaging systems, nets, chemical sensors, and mathematical models. Sound can reveal layers of animals that cameras cannot easily count. Nets collect specimens. Imaging systems observe fragile organisms that would be damaged during capture. Chemical measurements track oxygen, nutrients and carbon as they move through the water. Yet the twilight zone refuses to remain neatly arranged for observation. Many of its animals are only temporary residents at a given depth. During daylight, they remain in darker water where visual predators are less likely to find them. After sunset, they rise toward the surface to feed. Before dawn, they descend again. Across the global ocean, this nightly movement carries immense numbers of animals through hundreds of meters of water. The twilight zone is not a still layer beneath the surface. It is a living vertical highway, filling and emptying according to the changing light far above. Every evening, as sunlight fades from the surface of the ocean, an immense movement begins beneath it. Countless animals rise from deeper water toward the upper layers, travelling hundreds of meters through the darkening sea. Before the sun returns, many of them reverse direction and descend once more into the twilight below. This repeated movement is known as diel vertical migration. The word diel refers to a cycle lasting roughly one day, while vertical migration describes the upward and downward movement through the water column. It is one of the largest regular migrations on Earth. Unlike the movement of wildebeest across a plain or birds between continents, this migration is mostly invisible from the surface. Its participants are often small, widely dispersed, and hidden beneath deep water. Yet when their combined mass is considered, the scale becomes enormous. Lanternfish, bristlemouths, krill, copepods, squid, jelly-like animals, shrimps, and many other organisms take part. Different species travel different distances, occupy different depths, and respond to slightly different cues, but together they create a vast daily rearrangement of life across much of the global ocean. The most familiar pattern begins after sunset. During the day, many animals remain in deeper, darker water. There they are less visible to predators that hunt by sight. As evening approaches and the surface becomes dimmer, they begin to rise. Nearer the surface, food is more abundant. Phytoplankton grow in the illuminated water, and zooplankton gather to feed upon them. Small fish and crustaceans follow this concentration of life upward. The journey offers access to a richer feeding ground, but only under the protection of darkness. Before sunrise, the animals begin descending again. As light strengthens, remaining near the surface would make them easier to detect. Returning to the twilight zone reduces the risk from visually hunting fish, seabirds, and marine mammals. This produces a daily trade-off between hunger and safety. An animal that remains deep may avoid predators but miss valuable food. One that stays near the surface for too long may feed well but become part of somebody else's breakfast. Evolution has shaped a compromise in which many species travel upward when darkness lowers the danger and downward when daylight returns. The timing is guided largely by changing light intensity. Animals do not need to see the sun directly. Sensitive eyes and light-detecting cells can respond to subtle changes in brightness filtering down through the water. As sunset reduces the light above, migrants begin following a preferred level of darkness toward the surface. At dawn, that moving boundary of light descends. The animals descend with it, remaining beneath the level at which they would become too visible. The migration can begin before the surface appears completely dark to human eyes. Even small changes in light may provide a useful signal to animals adapted to conditions far dimmer than those we normally experience. Moonlight can alter the pattern as well. During bright moonlit nights, some animals remain deeper than usual or delay part of their ascent. Clouds may reduce the amount of light and allow them to rise farther. Seasonal changes in day length, water clarity, latitude, and weather can all influence the timing. Not every organism follows the standard schedule. Some species perform reverse vertical migration, remaining closer to the surface during daylight and moving deeper at night. This may help them avoid predators that are following the more common upward migration. Others travel only part of the distance, occupying intermediate depths rather than moving all the way to the productive surface layer. Some migrate only during certain life stages or seasons. Local oxygen conditions can also restrict movement. In regions with strong oxygen minimum zones, an animal may be physically unable to enter certain depths, even if food or safety would otherwise make the journey worthwhile. The ocean, therefore, does not rise and fall as one perfectly coordinated mass. It contains overlapping migrations, delays, reversals, and exceptions. The general movement is immense, but its details are shaped by the needs and limits of each species. Evidence for this hidden migration appeared clearly during the development of sonar. During the middle of the 20th century, ship operators noticed a strange reflecting layer beneath the surface. Sound pulses returned from what looked like a false seabed, sometimes several hundred meters above the true ocean floor. More strangely, this layer moved. It descended during the day and rose toward the surface at night. Researchers eventually realized that the sound was being reflected by dense concentrations of fish, crustaceans, squid, and other organisms. This phenomenon became known as the deep scattering layer. Gas-filled swim bladders in fish are especially effective at reflecting sound, although other bodies and tissues also contribute. The result is a biological layer large enough to appear on sonar as though the bottom of the ocean itself were moving up and down. The discovery revealed that apparently empty midwater could hold enormous populations. These migrating animals do not travel alone. Predators follow them. Tuna and swordfish may dive into deeper water in pursuit of fish and squid. Sharks can move between surface and twilight habitats. Dolphins, seals, and whales may descend hundreds of meters to reach concentrated prey. Some of these predators are commonly imagined as surface animals because that is where people see them breathe, leap, or gather near boats. Much of their feeding, however, can take place in the darker water below. The migration therefore connects the deep ocean with familiar surface life. Energy captured by phytoplankton passes into zooplankton and small fish, then into larger predators capable of travelling between very different environments. The movement also transports carbon. A migrating animal may feed near the surface during the night and descend before digesting the meal completely. At depth, it respires, releases waste, produces fecal material, or becomes prey. Carbon that entered the food web near the surface is therefore carried downward inside a living body. This is sometimes described as the active biological carbon pump. It differs from passive sinking because the material is not merely falling. Animals deliberately transport it through their own movement. Some carbon returns quickly to the water as carbon dioxide. Some becomes waste or dead tissue that sinks farther. Some is consumed by predators living at depth. Across enormous populations, these small transfers can have a meaningful influence on the movement of carbon through the ocean. The journey is not free. Travelling several hundred meters each day requires energy, particularly for small animals moving through water. They must feed enough near the surface to repay the cost of the ascent and descent. The colder temperatures at depth may help reduce metabolism during daylight hours. Remaining relatively inactive in dark water can conserve energy, while the nightly visit to the surface provides access to food. Even so, the distance is remarkable relative to body size. For a small copepod or lanternfish, moving hundreds of meters may be equivalent to a human making an exceptionally long commute twice every day, although the lanternfish is unlikely to complain about the traffic. The evolutionary benefit must be substantial for the behaviour to persist. Reduced predation during daylight combined with improved feeding after dark appears to outweigh the energetic cost for many species. As evening spreads across the planet, this process begins in one region after another. The surface may look calm, a ship may see only dark water and a faint horizon. Yet below, entire layers of animals are rising. Predators adjust their depth. Prey gather near food. carbon is carried downward. Sonar reflections shift upward through the water column. The open ocean reorganizes itself every night. Within this crowded vertical traffic, remaining unseen is essential. Animals rising toward faint surface light must avoid casting a silhouette. Others need to disguise their position from predators travelling beneath them. The migration is immense, but survival still depends on the individual body. For many twilight zone animals, that means using transparency, reflection, shape, and carefully controlled light to disappear within the moving darkness. In the twilight zone, survival often depends on controlling how much of the body can be seen from each direction. There are few rocks, plants, or reefs behind which an animal can hide. Open water surrounds it on every side. For small fish living hundreds of meters beneath the surface, camouflage must therefore be carried on the body itself. Lanternfish are among the most abundant vertebrates in this dim environment. Most are modest in size, commonly measuring only a few centimeters to a few tens of centimeters long. Yet their vast numbers make them an important part of ocean food webs and one of the dominant groups within the mesopelagic zone. The name comes from the light-producing organs arranged across their bodies. These organs are called photophores. A photophore may contain light-producing tissue, reflective layers, lenses, filters, and structures that control the direction of the glow. The result is not simply a bright spot. It is a biological lamp capable of producing light with a particular intensity, colour, and angle. Lanternfish often carry photophores in organised rows along their sides and undersides. The exact number and arrangement differ between species. To a scientist examining a specimen, these patterns can help with identification. To another lanternfish in the darkness, they may serve as signals showing which species, sex, or individual is nearby. The same organs can also help the fish disappear. During daylight, faint sunlight continues to filter down from the surface. An animal viewed from below appears against this dim overhead glow. Even if its body is dark, it can form a recognizable silhouette. Counter-illumination reduces that silhouette. A fish produces light along its underside, adjusting the glow until it resembles the natural light descending around it. To a predator beneath, the dark outline becomes less distinct because the animal no longer blocks the brightness above quite so clearly. The fish is not illuminating the surrounding ocean like a torch. It is producing only enough light to replace what its body would otherwise remove. This requires careful control. Too little light leaves a shadow. Too much creates a bright shape that may be equally obvious. Some animals can adjust their photophores as ambient brightness changes. Near the upper edge of the twilight zone, the background may be relatively bright during the day. At greater depth, or beneath cloudier water, much less light is needed. As the fish rises or sinks, its underside must remain closely matched to the changing environment. Counter-illumination is therefore not simple glowing, it is active brightness management. Marine hatchetfish use a similar strategy. Despite the rather dramatic name, most marine hatchetfish are small. Many species are only a few centimeters long. Their bodies are extremely thin from side to side and deeper from top to bottom, producing a shape that resembles the blade of a small hatchet. Their large, upward-facing eyes search the faint water above for prey and for the silhouettes of animals moving across the remaining surface light. The sides of the body are often silver and highly reflective. Photophores along the underside direct light downward, helping reduce the fish's outline when seen from below. Their narrow shape also reduces the visible area presented to an observer looking from certain angles. In open water, where hiding places are scarce, even a small reduction in silhouette can matter. Reflective sides provide a different kind of concealment. The light field in the twilight zone is unusual. Most remaining natural light comes from above, while very little arrives from below. Horizontally, the water can appear as a narrow band of diffuse blue or blue-green brightness. Mirror-like scales reflect this surrounding light. When viewed from the side, the fish may resemble the water beside it, rather than a solid object moving through it. Perfect reflection would not always work because a smooth mirror could create sharp flashes. Fish scales are arranged in ways that scatter light across several directions, softening the reflection and reducing obvious glints. Transparency offers another solution. Many jelly-like organisms, crustaceans, larvae and small fish allow light to pass through much of their tissue. This can make them difficult to detect in clear water. Complete transparency is rarely possible. Eyes contain pigments. Digestive organs contain food. Muscles and reproductive tissues bend and scatter light. Some animals conceal these visible structures with reflective surfaces or dark coverings while leaving the rest of the body largely clear. Dark pigmentation works under different conditions. A black body absorbs faint light rather than reflecting it. This is useful deeper in the water, where there is little natural illumination but brief flashes of bioluminescence might otherwise reveal a pale surface. Red coloration produces a similar effect because red wavelengths from the sun have already been absorbed far above. A deep red animal may appear almost black under the remaining blue light. Each strategy is suited to a different viewing direction and source of illumination. Silver helps from the side. Counter-illumination works from below. Dark colours reduce reflection during sudden flashes. Transparency allows faint light to pass through. No single disguise makes an animal invisible from every angle. Twilight zone predators must also find food in this difficult visual environment. Many have sensitive eyes capable of detecting weak light and small movements. Some possess long teeth, hinged jaws, or expandable stomachs. These features are often presented as signs of constant ferocity, but deep-sea hunting is usually less theatrical than it appears. Food may be scarce and widely scattered. A large mouth increases the range of prey that can be swallowed when an opportunity finally arrives. Expandable tissue allows an animal to handle an occasional large meal without carrying a permanently heavy body. Long teeth help secure slippery prey before it escapes. Much of the time, however, these fish are conserving energy, drifting, waiting, or swimming slowly through darkness. The dramatic equipment may be used only occasionally. Some dragonfish possess one of the most unusual lighting systems in the ocean. Most marine bioluminescence is blue or blue-green because these wavelengths travel efficiently through seawater. Many deep-sea animals are especially sensitive to them. Certain dragonfish can produce red bioluminescence and detect red light with specialized visual pigments. Many neighboring organisms cannot see those wavelengths well. The dragonfish can therefore illuminate nearby prey with a light that functions almost like a private search beam. The prey may remain unaware that it has been lit, while the predator receives enough reflected red light to locate it. Even this is not absolute invisibility. Some deep-sea animals have greater sensitivity to red than once assumed, and red light is absorbed relatively quickly by water. Its limited range may actually be useful, creating a close and discrete form of illumination. Biological light can perform many roles depending on where it appears and when it is used. A row of photophores can erase a silhouette. A patterned flash can identify a species. A glowing lure can attract prey. A sudden burst can startle a predator. A red beam can reveal an animal nearby. A deceptive signal can imitate food or confuse an attacker. The chemistry may be similar, but the message changes with position, timing, intensity, and color. As the descent approaches 1,000 meters, the last traces of sunlight become weaker. Counter-illumination still works while some downwelling brightness remains, but eventually there is no solar background left to match. Below that point, the sun no longer provides the ocean's visible reference. Reflective silver becomes less useful in permanent darkness. The carefully measured glow along an animal's underside no longer needs to imitate daylight. Light remains important, but almost all of it will now be produced by life itself. The final blue traces from the surface fade away, and the twilight zone gives way to permanent night. At approximately 1,000 meters beneath the surface, the last natural traces of sunlight disappear. The ocean enters the bathypelagic zone, more commonly known as the midnight zone. This region conventionally extends from around 1,000 metres to roughly 4,000 metres below sea level. Its boundaries are approximate, but the defining condition is clear. Under ordinary circumstances, no direct sunlight reaches these depths. Day and night continue far above, but they no longer produce a visible cycle here. Sunrise does not brighten the water, sunset does not darken it. Clouds, seasons, and passing storms leave no obvious trace in the surrounding light. The darkness is permanent, but it is not always complete. Small flashes appear and vanish. A row of glowing organs moves through the water. A lure hangs in front of a waiting mouth. A jelly-like animal produces a brief blue pulse before fading from view. Almost all visible light in the midnight zone is biological light, created by living organisms rather than delivered by the sun. Without that light, the water would appear entirely black. A human observer looking through an unlit submersible window would see nothing at all, even if an animal were swimming only a short distance away. The midnight zone is also cold. Temperatures commonly remain close to 4 degrees Celsius, although the exact value varies with depth, latitude, ocean basin, and the origin of the surrounding water mass. This cold can seem surprising beneath tropical seas. The surface may be warmed by intense sunlight, yet the water several kilometres below remains only a few degrees above freezing. The reason lies partly in the way the deep ocean is formed and circulated. Much of its water begins near high latitudes, where surface water becomes cold and dense. In regions around Antarctica and the North Atlantic, cooling sea ice formation and changes in salinity can make water dense enough to sink. These deep water masses then spread slowly through the world ocean. They carry the temperature and chemical characteristics of their source regions far beneath warmer surface layers. The deep ocean is therefore connected less directly to the tropical sun overhead than to cold surface conditions thousands of kilometres away. Food is limited as well. Nearly all ordinary organic matter begins in the sunlit zone, where phytoplankton use photosynthesis to build living tissue. Some of that material starts to sink, but much of it is eaten, broken apart, dissolved, or decomposed before reaching the midnight zone. Marine snow continues to fall, yet it is thinner and less nutritious than it was above. A particle may have been consumed several times, repackaged into waste, colonized by bacteria, and stripped of much of its useful energy during the descent. For the animals below, meals may be small, widely scattered, and unpredictable. These conditions favour energy conservation. Many midnight zone animals grow slowly and mature over long periods. Their muscles may be less powerful than those of fast predators near the surface. Movement is often deliberate and economical because swimming continuously in search of food could consume more energy than the food provides. Some animals wait almost motionless until prey approaches. Others drift with the water, using sensitive organs to detect movement nearby. A slow metabolism allows a creature to survive for longer between meals. When food finally appears, it may be too valuable to waste. Large mouths, hinged jaws, long teeth, and expandable stomachs allow certain deep-sea fish to capture prey that represents a substantial fraction of their own size. These features do not mean that every encounter becomes an extravagant feast. They simply increase the range of opportunities an animal can use. In a place where the next meal may not arrive soon, being slightly over-prepared is understandable. Populations can also be widely spaced. Suitable mates may be difficult to find, encouraging unusual reproductive strategies, strong chemical signalling, specialized light patterns, or the ability to store sperm after a rare encounter. The darkness alters the senses needed for survival, but vision does not become useless. Many animals possess eyes adapted to detect very small amounts of light. Some have large pupils and highly sensitive retinas. Others are specialized for recognizing the brief flashes and patterns of bioluminescence produced by prey, predators, or potential mates. An eye in the midnight zone is not searching for landscapes or sunlight. It is often searching for one moving point of blue light in an otherwise black field. Other senses can be equally important. Chemical receptors detect molecules released by food, damaged tissue, waste, or reproductive signals. Long antennae and delicate appendages respond to touch. The lateral line systems of fish sense vibrations and pressure changes caused by nearby movement. Some animals detect the gentle displacement of water created by a swimming body. Others wait for material to contact extended tentacles or feeding structures. In darkness, the water itself carries information. The midnight zone is sometimes imagined as the bottom of the ocean, but most of it remains open water. At 1,000 meters, the seafloor may still lie several kilometers farther below. An animal here can have darkness above, darkness below, and no solid surface anywhere nearby. It lives within the water column rather than upon the seabed. This distinction separates the bathypelagic environment from benthic habitats. The open midnight zone contains free swimming and drifting organisms, while the bottom may belong to the abyssal plain, a continental slope, a volcanic ridge, or some other landscape far beneath them. Pressure continues increasing throughout the descent. Near the upper boundary of the midnight zone, the surrounding pressure is roughly 100 times the atmospheric pressure at sea level. Near 4,000 meters, it approaches around 400 atmospheres. This immense force acts from every direction. Deep-sea animals survive because their tissues are largely water-filled and because their cells, membranes, enzymes and proteins are adapted to function under compression. The pressure is extreme, but it is stable. Unlike a storm at the surface, it does not arrive suddenly and then pass. It is simply part of the environment. In several respects, the midnight zone is more physically constant than the upper ocean. There is no direct sunlight cycle. Seasonal temperature changes are small. Waves do not reach these depths in their familiar surface form. Storm winds cannot suddenly stir the water around an animal living several kilometers below. Changes still occur through currents, falling material, migrating organisms, earthquakes, and distant disturbances, but the general environment remains cold, dark, and steady. That stability does not mean inactivity. Fish continue to hunt. Squid move through the water. Jelly-like organisms extend tentacles. Crustaceans feed on drifting particles. Animals find mates, release eggs, avoid predators, and respond to the faint arrival of organic material from above. Some species migrate between depths. Others remain within a narrow pressure and temperature range throughout their lives. Light appears in brief and carefully controlled forms. A flash may warn an attacker. A glowing lure may attract prey. A pattern of photophores may identify a possible mate. A cloud of luminous material may confuse a predator long enough for its target to escape. The midnight zone seems still only because its activity is dispersed across an enormous volume and hidden from ordinary sight. There is no daylight here, but there is communication. There are no visible horizons, but there are territories, encounters, pursuits, and signals. In this permanent night, living light becomes the nearest thing the ocean has to a visible language. In the permanent darkness of the deep ocean, light has not disappeared completely. It has simply changed its source. Instead of arriving from the sun, it is produced by living organisms through chemical reactions. This phenomenon is known as bioluminescence. Bioluminescence is different from reflected light. A silver fish near the surface may look bright because sunlight strikes its scales and returns toward the eye. A bioluminescent animal creates light within its own body, or with the help of microorganisms living inside it. It is also distinct from fluorescence. A fluorescent organism absorbs light of one wavelength, and quickly releases some of that energy as a different color. Without an outside source of illumination, fluorescence stops. Phosphorescence works in a related way but releases the stored energy more slowly, allowing a material to continue glowing after the original light has been removed. Bioluminescence requires no previous illumination. It is powered by chemistry. One of the central molecules involved is known as luciferin. When luciferin reacts with oxygen under suitable conditions, energy can be released as visible light. An enzyme called luciferase often helps control and accelerate this reaction. The names come from a Latin word associated with bringing light. They refer to broad roles rather than one universal chemical system. Different organisms use several chemically distinct luciferins and luciferases that evolved independently. There is no single bioluminescent recipe used throughout the ocean. In some animals, luciferin and luciferase remain separated until light is needed. When they are brought together, the reaction begins. Other organisms regulate oxygen supply, acidity, or cellular signals to control when and where the glow appears. An alternative mechanism involves photoproteins. These are prepared protein complexes that already contain the necessary light-producing components. A chemical trigger, often involving calcium ions, causes the complex to release light rapidly. Photoproteins can produce brief flashes with precise timing. This is useful for animals that need to respond instantly when touched, attacked, or disturbed. Some organisms manufacture all of the chemicals required for their own light. Others obtain essential luciferin molecules by eating organisms that have already produced them. Certain fish and squid rely instead on symbiotic bacteria. These bacteria live inside specialized light organs where they receive shelter and nutrients. In return, their continuous glow can be filtered, directed, covered, or exposed by the host animal. Maintaining a population of glowing bacteria may seem like an unusually elaborate arrangement, but the deep ocean has never been especially committed to simplicity. Bioluminescence serves many different purposes. A predator may use a glowing lure to attract prey within striking distance. A fish may shine light onto the water ahead, revealing small animals that would otherwise remain invisible. Rows of photophores can help members of the same species recognize one another in darkness. Light patterns may assist in finding mates. Their position, rhythm, color, and intensity can communicate identity without illuminating the entire animal. Bioluminescence can also provide camouflage. Counter-illumination allows an animal to match the faint light above, reducing its silhouette when viewed from below. The same chemical glow can therefore conceal one animal and advertise another. Its meaning depends on how it is used. Defense is especially varied. Some animals respond to disturbance by producing a sudden flash. The burst may startle a predator or interfere with its vision for a moment, creating time to escape. Others release clouds of luminous material into the surrounding water. A predator may attack the glowing cloud while the animal moves away through darkness. Certain squid and worms release glowing mucus that sticks to an attacker. This can make the predator more visible to larger hunters, which is not an especially reassuring development from the predator's point of view. Some organisms detach light-producing body parts. The discarded glowing structure continues moving or flashing while the rest of the animal retreats. Another strategy is known as the burglar alarm response. A small animal under attack produces a conspicuous display that may attract the attention of a larger predator. The larger predator may then attack the original pursuer. The glowing animal is effectively announcing that a burglary is taking place and hoping that something much larger will deal with the intruder. This behavior shows that producing light can alter not only a direct encounter, but the entire local food web. Studying these signals is difficult because conventional deep-sea vehicles bring powerful lights with them. Bright white lamps can frighten animals, attract them, blind their sensitive eyes, or change their behavior before researchers have observed what they were doing naturally. The marine biologist Edith Widder developed methods for watching deep-sea animals more quietly. Her research has focused on bioluminescence, visual ecology, and camera systems designed to observe without flooding the water with artificial light. One such approach uses dim red illumination, which many deep-sea animals detect poorly. Another uses electronic lures that imitate natural bioluminescent displays, attracting curious predators toward hidden cameras. These less intrusive systems have recorded animals behaving in darkness without immediately reacting to a brightly lit submersible. The Monterey Bay Aquarium Research Institute has also become a major centre for deep-water imaging and exploration. Its remotely operated vehicles, cameras, sensors, and long-term observations have revealed fragile animals that are difficult to collect intact. Gelatinous organisms are especially vulnerable to nets. A jelly, comb jelly, or siphonophore may be damaged beyond recognition during capture. Direct imaging allows researchers to study its shape, movement, feeding behaviour, and light production in the water where it lives. Observations suggest that roughly 3/4 of animals in the midwater ocean are capable of producing bioluminescence. The exact proportion varies with depth, region, and the groups being studied, but the general conclusion is clear. Living light is not a rare curiosity in the deep ocean. It is one of the dominant biological features of the environment. Most marine bioluminescence appears blue or blue-green. These wavelengths travel comparatively well through seawater. They also match the visual sensitivity of many deep-sea animals, whose eyes are adapted to detect the colours most likely to reach them. Producing blue light is therefore efficient both physically and biologically. It travels farther, and nearby animals are more likely to see it. Red bioluminescence is much rarer. Red wavelengths are absorbed quickly by seawater, and many deep-sea organisms have limited sensitivity to them. For certain dragonfish, however, this creates an advantage. They can produce red light and possess visual systems capable of detecting it. Nearby prey may be illuminated without recognizing that a searchlight has been turned upon them. Because red light travels only a short distance, it also provides a relatively private form of close-range illumination. The midnight zone is not filled with a continuous glowing haze. Light costs energy, and a constant display could reveal an animal to predators as easily as it reveals prey or mates. Instead, the darkness is interrupted by brief controlled events. A flash appears, communicates something, and vanishes. A lure glows only when needed. A pattern moves past and fades. A cloud of light expands through the water before slowly disappearing. The deep ocean remains dark, but never entirely silent in a visual sense. Its inhabitants have turned chemistry into signals, disguises, traps, warnings, and private conversations, creating a language made from moments of living light. The animals of the midnight zone often appear strange when they are brought into the bright light of a camera. Their mouths may seem too large, their bodies too soft, or their proportions entirely unfamiliar. Yet these shapes are not random. Each one reflects the physical conditions of a place where food is scarce. Pressure is immense, and encounters with prey or potential mates may be separated by long stretches of darkness. Few animals represent this world more clearly than the deep-sea anglerfish. The structure that gives the anglerfish its name begins as part of the dorsal fin. In many deep-sea species, the first fin spine has been modified into a long, flexible structure called the elysium. At its end sits a specialized lure known as the esker. The esker can glow, producing a small point of light in front of the fish's mouth. In some species, the illumination is created with the help of symbiotic bioluminescent bacteria living inside the lure. Other anglerfish use light-producing tissues and chemical systems of their own. The lure may be moved gently through the water, resembling a small animal or drifting fragment of food. A curious fish or crustacean approaches the glow, and the anglerfish waits almost motionless until the prey comes within range. The mouth can then open rapidly, creating suction that draws water and prey inward. Long teeth help prevent escape. Although anglerfish are usually illustrated as enormous monsters, many deep-sea species are relatively small. The female is often the larger animal, but even she may be only a few tens of centimetres long. The males of many pterygoid anglerfish are much smaller. This difference in size is known as sexual dimorphism, meaning that males and females of the same species have distinctly different physical forms. A male may spend much of his adult life searching for a female in a dark environment where individuals are widely scattered. His eyes and sense of smell can be specialized for locating her. In several ceratoid groups, the male bites the female when he finds her. Their tissues then fuse and their circulatory systems become connected. Over time, the male may lose much of his independent anatomy and remain attached as a permanent source of sperm. This reproductive strategy is known as sexual parasitism, although the relationship ultimately allows both animals to reproduce in an environment where finding another partner may be extremely difficult. Permanent attachment does not occur in every anglerfish. Some males attach only temporarily, while others remain fully independent. The dramatic fused pair is therefore one solution, among several rather than a universal rule. Its existence reflects a basic challenge of deep-sea life. When populations are sparse and visibility is almost absent, simply finding another member of the same species can become one of the most difficult parts of reproduction. Other midnight zone animals have adapted more strongly to the uncertainty of finding food. The gulper eel, also called the pelican eel, has a greatly enlarged mouth and a throat that can expand around prey. Its jaws are loosely hinged, while the skull is relatively small and delicate. The animal's long body narrows into a whip-like tail, which may end in a light-producing organ in some species. The tail can be moved through the water and may help attract or investigate nearby animals. The gulper eel's mouth is often described as capable of swallowing almost anything, but this exaggerates both its size and strength. Its jaws are light rather than powerful, and the animal is not built to consume objects without limit. The expanded mouth is better understood as a wide net. It allows the eel to capture small fish, crustaceans, squid, and other prey without requiring perfect aim in darkness. A large opening is useful when opportunities are rare. It does not remove the ordinary mechanical limits of digestion, body size, and jaw structure. The vampire squid has acquired an equally misleading reputation through its name. It is a deep-water cephalopod with dark reddish or black colouring, large eyes, and webbing stretched between its 8 arms. When threatened, it can turn this webbing outward, creating a cloak-like shape lined with soft spines called cirri. Despite its appearance, the vampire squid is not an aggressive hunter. It lives particularly well in oxygen minimum zones, where many other animals struggle to remain active. Its metabolism is unusually low, and its blood contains an efficient oxygen-carrying pigment called hemocyanin. These features allow it to survive in water containing very little dissolved oxygen. Rather than chasing large prey, the vampire squid feeds mainly on marine snow. It collects dead plankton, fecal material, mucus, and other drifting detritus using 2 long, retractable sensory filaments. The material is coated in mucus, drawn toward the mouth, and consumed slowly. Its rather theatrical name therefore belongs to an animal that spends much of its time gathering what is essentially deep-sea debris. Photophores cover parts of its body and can produce controlled flashes. When disturbed, the vampire squid may also release a cloud of glowing mucus from the tips of its arms. This luminous material can distract or confuse a predator, while the squid retreats into darkness. It does not use an ordinary ink cloud because dark ink would provide little concealment in an environment already without light. Many other midnight zone animals show equally specialized forms. Fangtooths possess long teeth relative to their body size, helping secure prey during rare encounters. Viperfish combine hinged jaws, needle-like teeth, sensitive eyes, and light-producing organs. Rat-tails, also called grenadiers, often swim close to the seafloor or through deep water using long tapering bodies and sensitive chemical systems to locate food. Deep-sea jellies and siphonophores take advantage of soft water-rich bodies. Siphonophores are not single animals in the usual sense, but colonies of specialized units, working together as one drifting organism. Some form extremely long chains containing feeding structures, reproductive sections, swimming bells, and tentacles. Their bodies can occupy a large volume without requiring heavy muscles or thick skeletons. Gelatinous tissue is close in density to seawater. This makes neutral buoyancy easier to maintain and reduces the energy needed to avoid sinking or rising. Gas-filled swim bladders become difficult to use at great depth because gas is compressed by pressure. Many deep-sea fish reduce these spaces or rely instead on oils, soft tissues, and body fluids for buoyancy. Their skeletons may be lightly mineralized, and their muscles may be less dense than those of fast surface predators. The result can look fragile outside the ocean, but fragility under ordinary atmospheric conditions does not mean poor adaptation to life at depth. Low food availability also favors reduced metabolic rates. Energy is spent cautiously. Growth may be slow, movement limited, and digestion prolonged. Expandable stomachs and flexible jaws allow some species to make use of a large meal when one arrives. The prey must still be physically manageable, but the animal can consume more than its ordinary body outline might suggest. Sensitive lateral line systems detect tiny movements in the surrounding water. Specialized enzymes continue working in cold conditions. Cell membranes maintain the flexibility needed for normal function, while dark, red, reflective, or transparent tissues reduce detection. Each feature addresses a specific difficulty. Large mouths respond to rare feeding opportunities. Soft bodies reduce energetic costs. Light organs help with hunting, defense, and communication. Unusual reproductive systems compensate for sparse populations. These animals are not distorted versions of surface life. They are precisely shaped for a different set of conditions. Yet every body, however soft or flexible, must still function beneath an extraordinary weight of water. Muscles must contract, proteins must fold, nerves must transmit signals, and membranes must remain intact. The deeper the ocean becomes, the greater the pressure surrounding every cell. Understanding the animals of the midnight zone therefore leads to a more fundamental question. How does life continue to work when the ocean is pressing inward from every direction? The deeper the ocean becomes, the more water there is overhead. Every additional meter adds another layer of weight, pressing downward and outward through the surrounding sea. This force is known as hydrostatic pressure. Hydrostatic pressure is produced by the weight of a fluid above a given point. In the ocean, it increases continuously with depth, because a deeper location supports a taller column of water. The useful approximation is that pressure rises by about 1 atmosphere for every 10 meters of sea water. This is added to the atmospheric pressure already acting on the ocean surface. At sea level, the human body experiences roughly 1 atmosphere of pressure from the air. At a depth of 10 meters, the total pressure is approximately 2 atmospheres. One comes from the atmosphere above the sea, and the second comes from the weight of the first 10 meters of water. By 200 meters, near the lower boundary of the sunlit zone, the surrounding pressure is roughly 20 atmospheres. At 1,000 meters, near the beginning of the midnight zone, it is close to 100 atmospheres. Across the deeper parts of the midnight and abyssal zones, pressure rises through several hundred atmospheres. At the average ocean depth, it is well over 300 times the atmospheric pressure experienced at sea level. At Challenger Deep, close to 11 kilometers beneath the surface, the pressure approaches roughly 1,100 atmospheres. This means that every small area of an exposed surface experiences an enormous inward force. Yet deep-sea animals do not immediately collapse beneath it. The reason is that pressure becomes dangerous mainly when there is a strong difference between the force outside an object and the pressure inside it. Most deep-sea animals contain a very high proportion of water. Water is only slightly compressible, and the fluid inside their tissues is held at nearly the same pressure as the seawater surrounding them. Because the pressure is balanced across their bodies, there is no empty interior for the ocean to crush inward. Gas-filled spaces are much more difficult. Gas compresses far more easily than liquid. A flexible container filled with air becomes smaller as pressure rises. This is why the air spaces in a human diver's lungs, ears, and diving equipment must be carefully managed during descent and ascent. Ordinary swim bladders present a similar problem for fish. These gas-filled organs help many shallow water species control buoyancy, but gas volume changes greatly under pressure. Some deep-sea fish reduce or lose their swim bladders. Others replace gas-based buoyancy with oils, soft tissues, reduced skeletons or other substances whose density remains closer to that of seawater. Foams and ordinary air-filled insulation are also compressed at depth. Materials that work well on land may become almost useless beneath several kilometres of water. Liquid-filled tissue avoids the most obvious crushing effect, but pressure still creates serious problems at the molecular level. Proteins must maintain specific three-dimensional shapes in order to work. Enzymes must bind correctly to other molecules. Cell membranes must remain flexible enough to transport nutrients and signals. Genetic material must be copied, repaired, and read. High pressure can disturb all of these processes. Organisms adapted to intense pressure are known as piezophiles. The name refers to life that prefers or requires elevated pressure. Some piezophilic microorganisms grow poorly at surface pressure because their enzymes, membranes, and cellular machinery are adapted specifically to deep conditions. Bringing them rapidly to the surface can disrupt or kill them, just as sending a surface organism into the deep would create severe stress. Cell membranes are especially sensitive. A membrane is not a rigid wall. It is a flexible layer built largely from fatty molecules. High pressure can make it more tightly packed and less fluid, interfering with the proteins embedded within it. Deep-sea organisms can alter the types of fatty molecules in their membranes, helping them remain flexible under both cold and pressure. Proteins face a related difficulty. Pressure can favour molecular arrangements that occupy less volume, potentially changing the shapes required for normal biological activity. Many deep-sea animals use small organic compounds known as piezolytes to stabilise proteins and preserve cellular function. One important example is trimethylamine N-oxide. In many marine fishes, the concentration of trimethylamine N-oxide increases with the depth at which the species normally lives. The compound helps counteract the destabilising effects of pressure on proteins. It is also associated with the familiar marine smell released when fish tissue begins to break down, although the living animal presumably considers protein stability the more important feature. There appears to be a practical limit to how much trimethylamine N-oxide fish can accumulate, while keeping their internal fluids chemically balanced. This may help explain why fish have not been found at the very deepest trench floors, even though invertebrates and microorganisms can survive farther down. Human exploration requires a very different strategy. A crewed submersible must preserve a small region of ordinary atmospheric pressure inside a structure surrounded by hundreds of atmospheres outside. The occupied compartment is usually built as a thick pressure sphere. A sphere distributes force evenly across its surface and avoids the weak corners that would occur in a box-shaped cabin. Modern pressure spheres may be made from titanium alloys or other strong materials chosen for their ability to resist compression, corrosion, and repeated cycles of descent and ascent. Ceramic components can be used where high strength and resistance to compression are valuable. Windows, when included, must be carefully shaped and constructed from thick transparent materials capable of carrying immense loads. Robotic vehicles avoid the need for a human-sized atmospheric cabin, but their electronics still require protection. Some components are placed inside pressure-resistant housings. Others are immersed in oil so that the pressure inside and outside remains balanced. Oil-filled electronics contain little or no compressible air. As the vehicle descends, the surrounding pressure is transmitted through the oil without crushing the internal components. Pressure-tolerant batteries, connectors, cables, cameras, and motors must all continue functioning under cold, corrosive, high-pressure conditions. Buoyancy creates another engineering problem. Ordinary foam would collapse, so deep-sea vehicles often use syntactic foam. Syntactic foam contains countless tiny hollow spheres, commonly made from glass or ceramic material, embedded within a strong resin. The microscopic spheres trap buoyant space while resisting compression far more effectively than conventional foam. Woods Hole, Oceanographic Institution's human-occupied vehicle. Alvin uses a titanium personnel sphere and specialized buoyancy materials to carry scientists into the deep ocean. Alvin has been used to investigate hydrothermal vents, deep-sea geology, shipwrecks, and marine ecosystems. Its current depth capability reaches several kilometers below the surface, allowing direct observation of much of the seafloor. The remotely operated vehicle Jason is connected to a surface ship by a cable carrying power, control signals, and data. It can remain underwater for long periods while pilots and scientists operate it from above. Jason's robotic arms collect rocks, sediments, fluids, and organisms. Its cameras reveal environments that would otherwise remain hidden, while its instruments measure temperature, chemistry, and physical conditions. Every part of such a vehicle must be carefully designed and tested. If a pressure vessel fails at great depth, the external water enters extremely rapidly because of the enormous pressure difference. The failure is sudden and severe. Deep ocean engineering therefore depends on conservative design, material testing, repeated inspection, carefully calculated safety margins, redundancy, and strict operating procedures. Pressure cannot be negotiated with or persuaded to wait until a repair is convenient. It remains constant, patient, and entirely unimpressed by human confidence. For deep-sea life, pressure has shaped membranes, enzymes, skeletons, tissues, and methods of buoyancy across evolutionary time. For human explorers, it has shaped spheres, housings, materials, batteries, windows, and every mechanical connection. Beneath the increasing weight of the water, biology and engineering face the same basic requirement. Every structure must remain functional, while the ocean presses inward from every direction. With that pressure understood, the deep sea floor becomes easier to imagine. It is not merely dark and cold. It is a place where life, rock, water, and machinery all exist under forces hundreds of times greater than those at the surface. At first, the deep sea floor appears to offer very little support for life. There is no sunlight, the surrounding water is close to freezing, and most food arrives only as a thin fall of organic material from far above. Then, across certain areas of tectonically active seabed, the darkness is interrupted by heat, minerals, and dense communities of living organisms. These are hydrothermal vents. A hydrothermal vent system begins when seawater enters cracks and fractures in the oceanic crust. The water sinks beneath the seabed, moving through spaces within hot volcanic rock. As it descends, it is heated by the surrounding crust and by magma lying deeper below. High temperature and pressure allow the water to react strongly with the rock, dissolving minerals and changing its chemical composition. The altered fluid becomes hotter and more buoyant. It rises back toward the seafloor and escapes through openings in the crust. The result is a circulation system driven by heat. Cold sea water enters through cracks. Hot mineral-rich fluid returns through vents. The process can continue as long as there is sufficient heat below and a pathway through the rock. Hydrothermal vents are commonly associated with mid-ocean ridges, where tectonic plates move apart and new oceanic crust forms. They also occur in volcanic regions, back-arc basins, and other places where magma lies close enough to the seafloor to heat circulating water. Their existence is closely connected to the theory of plate tectonics. The global mid-ocean ridge system is not merely an underwater chain of mountains. It is an active boundary where Earth's plates separate, magma rises, and the crust is continuously created, fractured, cooled, and altered. For much of the 20th century, scientists suspected that seawater and hot, oceanic crust might interact in this way. Direct evidence, however, remained difficult to obtain. That changed during an expedition to the Galapagos Rift in 1977 aboard the research vessel Nor. The expedition brought together geologists, geochemists, geophysicists, biologists, engineers, and submersible specialists. Among the scientists involved were Robert Ballard, Richard von Hertzen, Jack Corliss, John Edmund, Tjeerd van Andel, Tanya Atwater, Jack Diamond, Louis Gordon, and many other collaborators. Their work combined observations of seafloor geology with measurements of temperature and seawater chemistry. One of the important tools used during the search was Angus, a towed camera system whose name came from the phrase acoustically navigated geological underwater survey. Angus was lowered behind a ship and moved above the seafloor, taking photographs in darkness. Its cameras helped researchers identify areas where unusual deposits, pale shells, and dense communities of organisms appeared around warm water emerging from the seabed. The human-occupied submersible Alvin then allowed scientists to descend directly to the Galapagos Rift. Through Alvin's small viewing ports, they observed warm hydrothermal water flowing from cracks and saw biological communities far richer than expected at such depth. Large clams, mussels, crabs, and other animals surrounded the vents. The discovery was startling because the ecosystem existed far below the reach of sunlight. The first vents observed in 1977 released warm water rather than the extremely hot fluids later associated with the most dramatic vent systems. In 1979, scientists exploring the East Pacific Rise encountered black smokers. These vents discharge dark plumes from tall mineral chimneys. The fluid can approach 400 degrees Celsius, yet it does not boil in the ordinary way. At the surface, water boils when its vapor pressure becomes equal to the surrounding atmospheric pressure. Deep beneath the ocean, the external pressure is hundreds of times greater. This raises the temperature at which water can form vapor. As a result, vent fluid can remain liquid at temperatures that would produce violent boiling in an ordinary kitchen, although taking a kettle to the bottom of the Pacific would introduce several other practical difficulties. The fluid leaving a black smoker is not naturally black. It becomes dark as it mixes with cold seawater. While travelling through the hot crust, the water dissolves metals and sulfur-bearing compounds. When the fluid escapes and cools rapidly, these dissolved materials can no longer remain in the same form. Particles of metal sulfides and other minerals precipitate from the water, producing the dark plume. Some of those particles settle around the vent opening. Layer by layer, they build chimneys that can grow several meters tall. The structures are fragile and temporary on geological timescales. They may collapse, become blocked, or be abandoned as underground pathways shift. The biology surrounding them depends not on sunlight but on chemical energy. Chemosynthesis is the biological production of organic matter, using energy released by chemical reactions. At hydrothermal vents, bacteria and archaea can obtain energy by oxidizing hydrogen sulfide, hydrogen, methane, iron, and other reduced compounds carried in vent fluid. They use this energy to convert carbon dioxide into organic material. The principle resembles photosynthesis at a high level. In both cases, organisms capture an external source of energy and store it within chemical bonds. The difference lies in the energy source. Photosynthesis uses light. Chemosynthesis uses reactions between chemical substances. These chemosynthetic microorganisms form the energetic foundation of vent communities. Some grow freely on rocks and chimney surfaces, others form thick microbial mats. Many live in close symbiosis with animals. One of the most famous vent animals is the giant tube worm Riftia pachyptila. Adult Riftia can grow more than a meter long and live inside a white protective tube. A bright red plume extends into the surrounding water and absorbs oxygen, carbon dioxide, and hydrogen sulfide. The adult animal has no conventional mouth, stomach, or digestive tract. Instead, much of its internal body is occupied by an organ called the trophosome. This tissue contains enormous numbers of chemosynthetic bacteria. The tube worm transports the necessary chemicals to the bacteria through its blood. The bacteria use chemical energy to produce organic matter, which nourishes the host. The relationship allows the tube worm to live without eating in the familiar sense. Vent mussels and clams may also house chemosynthetic microbes within their tissues. Shrimp can graze on bacteria or maintain microbial communities on specialized body surfaces. Crabs, snails, worms, fish, amphipods, bacteria, and archaea occupy different parts of the habitat. Not every vent community looks the same. Some are dominated by giant tube worms, others contain large numbers of shrimp, mussels, snails, or specialized crustaceans. The composition depends on water chemistry, temperature, depth, geological setting, and the history of the vent field. A vent rich in hydrogen sulfide may support different microorganisms from one dominated by methane or hydrogen. Hot fluid close to a chimney creates one habitat, while cooler mixed water several meters away creates another. The ecosystem is arranged along steep chemical and temperature gradients. Water emerging from a vent can be hot enough to damage living tissue, yet only a short distance away it mixes with near-freezing seawater. Animals position themselves where the temperature and chemical supply remain tolerable. Vent ecosystems are sometimes described as being completely independent of the sun, but that is not entirely accurate. Their primary production does not require sunlight. Chemosynthetic microbes can build organic matter using energy from vent chemistry. However, many of the reactions they use depend on oxygen or other oxidizing chemicals present in seawater. Much of that oxygen ultimately comes from photosynthesis near the surface. Vent animals also release larvae into the surrounding ocean. Those larvae must disperse through ordinary seawater to locate another active vent field. Some species feed partly on material arriving from outside the vent system, while predators and scavengers move between vent and non-vent habitats. The communities are therefore connected to the wider ocean, even though their local foundation is chemical rather than solar. The discovery of hydrothermal vents transformed biological understanding. Before 1977, complex ecosystems were generally expected to depend directly or indirectly on sunlight falling nearby. The vent communities demonstrated that dense animal life could flourish in complete darkness, supported by microorganisms using energy from reactions within Earth's crust. Sunlight remained central to most life on the planet, but it was no longer the only possible starting point for an ecosystem. At the bottom of the ocean, chemistry could take the place of daylight. Around cracks in volcanic rock, bacteria became the equivalent of plants, mineral chimneys became crowded habitats, and the dark seafloor revealed an oasis powered by the internal heat of Earth. Hydrothermal vents show that sunlight is not the only source of energy capable of supporting life. Around modern vents, microorganisms use chemical reactions to produce organic matter, creating the foundation for communities of tube worms, mussels, crabs, and other animals. This raises a deeper question. Could similar environments have helped life begin on early Earth? It is important to separate what is known from what remains uncertain. Modern hydrothermal vents unquestionably support life. The idea that the first living systems originated in or near ancient vents is a scientific hypothesis, not an established fact. The best-known hydrothermal systems are black smokers. These release extremely hot, mineral-rich fluids from volcanic sea floor. Their fluids are often acidic and can approach 400 degrees Celsius, although the immense surrounding pressure prevents ordinary boiling. Black smokers provide chemical energy and useful minerals, but their high temperatures may also destroy fragile organic molecules. For this reason, many origin of life researchers focus instead on cooler alkaline hydrothermal systems. One important example is the Lost City hydrothermal field in the Atlantic Ocean. Its pale carbonate towers differ greatly from the dark chimneys of black smokers. The fluids are alkaline and generally much cooler, often below 100 degrees Celsius. Lost City is powered mainly by a geological process called serpentinization. Serpentinization occurs when seawater reacts with iron-rich rocks from Earth's mantle. These reactions change the original minerals, release heat, and can produce hydrogen. The resulting vent fluids are chemically very different from the surrounding seawater. This contrast creates chemical disequilibrium, meaning that two nearby environments contain substances capable of reacting and releasing energy. The alkaline hydrothermal vent hypothesis is closely associated with the geologist Michael Russell and has been developed with researchers including William Martin. The hypothesis proposes that tiny mineral pores inside ancient alkaline vents may have acted as natural compartments. Instead of useful molecules being immediately diluted throughout the ocean, they could have accumulated inside small chambers within the vent structure. These mineral compartments may also have separated alkaline vent fluid from the more acidic surrounding ocean. That separation could have maintained natural chemical gradients. One particularly important example is a proton gradient. A proton gradient is a difference in the concentration of hydrogen ions across a boundary. When more hydrogen ions are present on one side than the other, the imbalance can store usable energy. Modern cells still depend on this principle. They move hydrogen ions across membranes and then allow them to flow back through a molecular machine called adenosine triphosphate synthase. This process helps produce adenosine triphosphate, the molecule cells use as an immediate source of chemical energy. The alkaline vent hypothesis suggests that early chemical systems may initially have used proton gradients, created naturally by geology. Only later would primitive organisms have evolved membranes and molecular machinery capable of producing and controlling those gradients themselves. Minerals may also have assisted early reactions. Iron-sulfur minerals found around vents can act as catalysts, allowing certain chemical reactions to occur more easily. They also provide surfaces on which molecules can gather rather than remaining widely dispersed in seawater. Iron and sulfur remain important in modern biology. Many proteins involved in metabolism and energy transfer contain iron-sulfur clusters. This does not prove that life began on mineral surfaces, but it provides an interesting connection between hydrothermal chemistry and the machinery found inside living cells. A related proposal is the iron-sulfur world hypothesis, developed by the chemist Günther Wechtershäuser. Wechtershäuser suggested that early metabolism may have developed as a network of chemical reactions occurring on iron-sulfur mineral surfaces. In this view, organized metabolism may have appeared before free-living cells or fully developed genetic systems. The iron-sulfur world hypothesis and the alkaline vent hypothesis overlap, but they are not identical. Michael Russell's model places particular emphasis on mineral compartments and natural proton gradients, while Wechtershäuser focused more strongly on surface-based metabolic reactions. Hydrothermal environments offer several possible advantages for the origin of life. They can provide chemical energy over long periods. Mineral surfaces may encourage reactions. Small pores can concentrate molecules and create compartments. Hydrogen produced by serpentinization can react with carbon dioxide, potentially helping form carbon-based compounds. Water and rock would also have protected delicate chemistry from intense ultraviolet radiation at Earth's surface. Yet the hypothesis faces serious difficulties. The ocean can dilute molecules rapidly. Heat may destroy some useful compounds. Primitive membranes may not remain stable in alkaline or mineral-rich conditions. The formation of genetic polymers, including early forms of ribonucleic acid, may also be difficult in seawater. Researchers must explain how simple molecules became organized into systems capable of storing information, reproducing, and evolving. Another problem is independence. A primitive system living inside a mineral pore would eventually need to develop its own membrane and chemical machinery. Otherwise, it would remain permanently dependent on the vent's natural structure and gradients. Laboratory experiments have shown that minerals, hydrogen, carbon dioxide, and vent-like conditions can support parts of plausible prebiotic chemistry. Researchers have produced simple organic compounds and demonstrated reactions that may have contributed to early metabolism. However, no experiment has created a complete living cell from hydrothermal vent chemistry. Other possible birthplaces for life remain under investigation. Shallow pools may have concentrated molecules through repeated cycles of evaporation and refilling. Volcanic lakes could have supplied heat and reactive minerals. Coastlines offered changing conditions involving tides, wetting, drying, and sunlight. Ice may have protected molecules while concentrating them inside narrow liquid channels. Impact craters could have created temporary hydrothermal systems in fractured rock. Life may even have emerged through several connected environments rather than within one perfect location. The question is also important beyond Earth. The National Aeronautics and Space Administration studies hydrothermal chemistry when considering Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both are thought to contain oceans beneath thick shells of ice. If those oceans interact with rocky seafloors, hydrothermal reactions may provide chemical energy even though sunlight cannot reach the water. That does not show that life exists there. It simply means that some potentially useful conditions may be present. Hydrothermal vents remain one of the strongest scientific hypotheses for the origin of life, because they bring together water, minerals, chemical energy, hydrogen, carbon compounds, and natural compartments. They offer a plausible connection between geology and biology. But the evidence is not yet conclusive. Life may have begun at an alkaline vent, in a shallow pool, beneath ice, beside a volcanic lake, or through a sequence of environments no longer preserved. For now, hydrothermal vents remain a serious and productive possibility, not a settled answer to where life first began. The concentrated activity of a hydrothermal vent can disappear surprisingly quickly. A short distance from its warm fluid, mineral chimneys and dense animal communities, the seafloor may return to a landscape that seems almost empty. At depths of roughly 4,000 to 6,000 meters, much of the ocean enters the abyssal environment. Here, broad regions of the seabed form abyssal plains, some of the largest and flattest habitats on Earth. The underlying oceanic crust is not naturally smooth. It begins as irregular volcanic rock shaped by lava flows, fractures, ridges, and smaller hills. Over millions of years, however, fine material settles through the water and gradually covers this rough surface. Clay carried from continents, microscopic shells, volcanic ash, mineral dust, and the remains of marine organisms accumulate in thin layers. Sediment fills depressions and softens the contours of the crust beneath it. The resulting plains are not perfectly level, but their slopes are often extremely gentle. They can extend across enormous areas with little obvious change in the landscape. Seen through the narrow beam of a remotely operated vehicle, the abyss may appear lifeless. Pale sediment stretches beyond the reach of the lights, interrupted only occasionally by a small animal, track, burrow, or mound. This apparent emptiness is partly an effect of scale. The abyssal plain is not sterile. Its inhabitants are simply distributed thinly across an immense habitat, because food is scarce. A camera may travel for some distance before encountering a large animal, while the sediment beneath it contains microorganisms and small invertebrates that are much harder to see. The physical conditions are severe but relatively stable. There is no sunlight. Water temperatures commonly remain close to freezing, often between about 2 and 4 degrees Celsius. Pressure reaches several hundred times the atmospheric pressure at sea level. Currents are usually weaker than those near the surface, although deep water is never completely motionless. Slow circulation carries oxygen, dissolved chemicals, sediment, and occasional particles across the plain. The main limitation is food. Most abyssal life depends ultimately on organic matter produced in the sunlit ocean far above. As phytoplankton, animals, and waste begin to sink, they form the loose fall of material known as marine snow. Marine snow contains dead plankton, fecal pellets, mucus, discarded feeding structures, shells, fragments of tissue, mineral dust, and microorganisms growing on the particles. The descent may take days, weeks, or longer, depending on the size and density of the material. During that journey, bacteria and other microbes break down much of the organic matter. Zooplankton consume it. Larger particles are fragmented, dissolved, or repackaged into waste. By the time marine snow reaches the abyssal floor, only a small fraction of the material that left the surface remains. This faint supply supports communities adapted to gathering almost every usable trace. Sea cucumbers move slowly across the sediment, swallowing mud and extracting organic particles from it. Brittle stars raise their flexible arms into the water or search the seabed for food. Polychaete worms burrow through the sediment, while amphipods and isopods scavenge fragments of organic material. Sponges filter particles from the passing water. Xenophyophores are giant single-celled organisms that build complex structures from sediment and collected particles. Although each is technically one cell, some grow large enough to be clearly visible in deep-sea photographs. Rat-tailed fish, also called grenadiers, swim just above the bottom, using sensitive chemical systems to locate carrion, worms, crustaceans, and other small prey. Many abyssal animals are deposit feeders. Rather than hunting a particular organism, they process sediment and remove the small amount of edible material mixed within it. Others are scavengers, waiting for something larger to arrive. Across parts of the abyssal plain lie dark, rounded objects known as polymetallic nodules. These mineral deposits form around small centres such as rock fragments, shell pieces, or shark teeth. Over extremely long periods, layers rich in manganese and iron accumulate around the centre. The nodules may also contain nickel, cobalt, copper, and other elements of commercial interest. Their growth is exceptionally slow. In many areas, they increase in size by only a few millimeters over 1 million years. The nodules are not living organisms, but they create habitat. Sponges, corals, worms, and microorganisms may attach to their hard surfaces in regions where most of the surrounding seabed consists of soft sediment. This has made proposed deep-sea mining scientifically controversial. Mining vehicles could remove nodules while disturbing or compacting the sediment beneath them. Their movement may create plumes of fine particles that spread through the surrounding water and settle elsewhere. Noise, vibration, artificial light, and the removal of hard surfaces could affect animals beyond the immediate mining path. Recovery is particularly uncertain because abyssal ecosystems operate slowly. Nodules require millions of years to form, and many deep-sea animals grow gradually, reproduce infrequently, or remain poorly studied. Researchers therefore cannot confidently predict how long a disturbed community would need to recover, or whether some specialized habitats could return at all. Most of the abyss survives on a thin and steady supply of marine snow. Occasionally, however, an enormous concentration of food arrives all at once. When a whale dies near the surface, its body may float while gases accumulate inside it. Eventually, the carcass can sink and come to rest on the deep sea floor. This is known as a whale fall. Compared with the ordinary food supply of the abyss, a whale carcass is an extraordinary delivery of organic matter. It can support a succession of communities over years or even decades. Large scavengers often arrive first. Hagfish, sharks, rat-tailed fish, amphipods, and other animals remove soft tissue from the carcass. As the remains become smaller, enrichment opportunist animals gather in the nutrient-rich sediment around the bones. Worms and crustaceans feed on remaining tissue, while microbial activity increases. Later, fat stored inside the bones can support bacteria that produce hydrogen sulfide. Sulfide-dependent microorganisms and animals associated with them may then colonize the site. Bone-eating worms from the genus Osedax play a particularly unusual role. They lack conventional mouths and digestive systems. Instead, Root-like tissues grow into the bone, where symbiotic bacteria help them obtain nutrients. Marine ecologist Craig Smith and researchers from the University of Hawaii have been central to modern scientific understanding of whale falls. Researchers from the Monterey Bay Aquarium Research Institute and the National Oceanic and Atmospheric Administration have also used submersibles, remotely operated vehicles, and long-term observations to study these communities. A whale fall can be imagined as a temporary island of abundance surrounded by a much poorer landscape. It is important, however, not to exaggerate its wider role. Whale carcasses are rare and unevenly distributed. They do not provide the ordinary food supply for the entire abyss. Most animals still depend on small particles sinking from above, material within the sediment, or occasional remains much less substantial than a whale. The abyssal plain is therefore shaped by scarcity, patience, and distance. Food arrives in tiny fragments, with rare moments of abundance. Animals move slowly, communities are widely spaced, and the landscape changes on timescales, difficult for humans to observe directly. For long stretches, the seabed remains broad and almost level. Then the ground begins to tilt. The plain gives way to steeper slopes. Sediment may slide downward. The crust bends beneath the pressure of another tectonic plate. After thousands of kilometers of relative flatness, the seafloor suddenly descends into a trench, carrying the ocean into its deepest and most extreme environment. Below approximately 6,000 meters, the ocean enters its deepest region. This is the Hadal Zone, named after Hades, the underworld of ancient Greek mythology. Unlike the broad abyssal plains above, the Hadal Zone does not form one continuous layer around the planet. It exists mainly inside deep, narrow ocean trenches. These trenches form where tectonic plates meet at subduction zones. At a subduction zone, one plate bends and descends beneath another, carrying part of Earth's crust back into the mantle. The downward curve creates a long depression in the seafloor. The same process can produce powerful earthquakes, chains of volcanoes, and, when the seabed moves suddenly, destructive tsunamis. Trenches are therefore not merely deep holes. They are active geological boundaries shaped by the slow movement of the planet's outer shell. The best-known example is the Mariana Trench in the western Pacific Ocean. It lies east of the Mariana Islands and extends for more than 2,000 kilometers. Within it is Challenger Deep, the deepest surveyed region of the global ocean. Measurements place the lowest part at approximately 10,900 meters below sea level. The exact figure varies slightly between surveys. Sound travels at different speeds depending on water temperature, salinity, and pressure. Instruments follow slightly different routes, and Challenger Deep contains more than one depression that may be described as its lowest point. The broad conclusion, however, is not in doubt. The bottom lies close to 11 kilometers beneath the surface. Mount Everest rises approximately 8,849 meters above sea level. If it were placed inside Challenger Deep, its summit would remain beneath more than 2 kilometers of water. The bottom also lies deeper than the normal cruising altitude of many commercial aircraft. A passenger aircraft passing above the sea could therefore be closer to the trench floor than a ship floating directly over it. The physical conditions at this depth are extreme. There is no sunlight. Temperatures remain only a few degrees above freezing. Pressure approaches roughly 1,100 atmospheres, meaning that the surrounding force is more than 1,000 times greater than atmospheric pressure at sea level. The trench walls can be steep and unstable. Earthquakes, landslides, and sediment flows may carry material downward. Organic particles sinking across a wide area can also be funneled toward the trench axis. This means that some Hadal locations may receive more food than a similarly deep, flat surface would receive. Even so, the environment remains cold, dark, isolated, and severely limited in fresh organic material. Life persists there. Hadal amphipods scavenge fallen material and may gather rapidly around bait placed by scientific landers. Sea cucumbers move across the sediment, consuming mud and extracting organic particles. bristle worms burrow through the seafloor. Isopods, microbes, and xenophyophores occupy sediments and surfaces throughout the trenches. Some microorganisms live within the mud, where they help break down organic matter and cycle carbon, nitrogen, sulfur, and other elements. Snailfish are among the most recognizable hadal vertebrates. Their bodies are soft, lightly built, and without gas-filled swim bladders. Several species live thousands of meters below the surface, feeding on amphipods and other small animals. However, fish do not appear to survive at the very deepest trench floors. The deepest confirmed fish observations have occurred a little beyond 8,000 meters. Below this range, increasing pressure may disrupt cellular chemistry beyond the point that fish can compensate. One possible limit involves trimethylamine N oxide, a compound that helps stabilize proteins under pressure. Many marine fish accumulate more of it as their normal habitat becomes deeper. At extreme concentrations, however, it may interfere with the balance of water and dissolved substances inside the body. This may help create a physiological depth limit for vertebrate fish. Invertebrates and microorganisms use different adaptations and can survive deeper. Hadal animals generally contain few compressible gas spaces. Flexible, water-rich bodies allow pressure to remain balanced inside and outside their tissues. Their cell membranes contain specialized fats that remain functional under cold and compression. Pressure-stabilizing molecules help proteins keep the shapes required for normal activity. Many species grow slowly, conserve energy, and feed opportunistically. They consume marine snow, carrion, sediment, microbes, and material delivered by currents or landslides. The deepest ocean may appear empty, but its inhabitants are adapted to use almost anything edible that arrives. Humans first reached Challenger Deep in 1960. The Swiss oceanographer Jacques Piccard and United States Navy Lieutenant Don Walsh descended aboard the bathyscaphe Trieste. Trieste differed greatly from a modern streamlined submersible. Its main float was filled with gasoline, which is lighter than seawater and only slightly compressible. A thick steel pressure sphere hung beneath the float and contained the two occupants. The cabin was extremely small, with little room to move during the descent. Heavy iron weights pulled the vessel downward. To return to the surface, Trieste released the weights, allowing the buoyant gasoline-filled float to carry it upward. The descent took several hours. Near the bottom, the men observed a pale sediment surface through a small window and remained there for only a short time before beginning their ascent. Their journey proved that a crewed vehicle could survive the pressure at the deepest known part of the ocean. More than half a century later, filmmaker and explorer James Cameron made the first solo descent to Challenger Deep. In 2012, he travelled aboard Deep Sea Challenger, a narrow vertical vehicle designed for full ocean depth exploration. The submersible used modern syntactic foam, batteries, cameras, robotic equipment, and a compact pressure sphere. Cameron spent several hours near the bottom collecting images and observations. Beginning in 2019, explorer Victor Vescovo completed repeated dives aboard Limiting Factor. Unlike many earlier deep diving vehicles, Limiting Factor was designed for repeated journeys to full ocean depth, rather than a single experimental descent. Its titanium pressure sphere carried two people, allowing scientists and explorers to visit trenches in several ocean basins. In 2020, former National Aeronautics and Space Administration astronaut and oceanographer Catherine Sullivan descended to Challenger Deep aboard Limiting Factor. She became the first person to have both travelled into space and reached the deepest known point in the ocean. The number of people who have visited Challenger Deep remains very small, although it continues to grow as new expeditions are completed. Robotic exploration is far more common. Deep-sea landers can be released from ships and allowed to fall to the bottom, where they record video, collect water, measure chemistry, or attract scavengers with bait. Autonomous underwater vehicles follow programmed routes without remaining attached to a ship. Remotely operated vehicles receive power and commands through cables, although working at full ocean depth requires exceptionally long and strong systems. Pressure-resistant cameras, sonar instruments, sediment samplers, and water bottles allow scientists to observe the environment without placing people inside a pressure sphere. The National Oceanic and Atmospheric Administration contributes mapping, exploration, and scientific coordination. Woods Hole Oceanographic Institution develops vehicles and instruments for deep-sea research. The Schmidt Ocean Institute supports expeditions using advanced sonar, robotic vehicles, and open scientific data. The Japan Agency for Marine Earth Science and Technology has conducted major trench research with submersibles, landers, and deep-sea drilling systems. University teams from many countries study hadal biology, geology, chemistry, pressure adaptation, and sediment processes. Their findings have also revealed an uncomfortable connection to the surface. Plastic fibers, fragments, and other human-made contaminants have been detected in hadal sediments and animals. Chemical pollutants have reached trenches that once seemed completely isolated from ordinary human activity. The deepest places on Earth are remote, but they are not sealed away from the rest of the planet. Water circulates, particles sink, animals feed, contaminants travel through food webs and settle into sediment. Reaching the bottom, therefore, does not mean reaching a world untouched by events above, nor does it mean that the ocean has been fully understood. A successful descent reveals only a tiny patch of seafloor. A camera records only the animals that happen to pass within its lights. A sediment sample represents one location at one moment. Many trenches remain poorly mapped. Numerous species have never been described. Chemical cycles are still being measured, and the movement of water and sediment through these narrow environments remains incompletely understood. At Challenger Deep, the downward journey finally ends. There is solid ground beneath the water, almost 11 kilometers below the familiar ocean surface. Yet arriving at the bottom does not complete the map. It does not identify every organism or explain every process taking place in the darkness. The deepest point is not the end of discovery. It is simply the lowest place from which the unknown can still extend outward in every direction. The journey to the bottom of the ocean begins at a surface that never truly stands still. Wind moves across it, waves carry energy, sunlight warms the upper water, and gases pass constantly between the sea and the atmosphere. Below that moving boundary lies the sunlit zone, where coral reefs form intricate living structures and microscopic phytoplankton capture the energy of sunlight. These drifting organisms support marine food webs, produce a large share of the oxygen generated on Earth each year, and draw carbon dioxide into living tissue. As the descent continues, the familiar colours of the surface begin to disappear. Red fades first, followed by orange and yellow. The remaining light becomes increasingly blue, then dim until the ocean enters the twilight zone. Here, lanternfish, hatchetfish, squid, crustaceans, and countless smaller animals rise toward the surface after sunset and return to deeper water before dawn. This diel vertical migration moves carbon through the water column as animals feed above and respire, release waste, or become prey below. Farther down, sunlight vanishes completely. The midnight zone is cold, dark, and under immense pressure. Food becomes scarce, and the animals living there conserve energy, sense movements through the water, follow chemical traces, and produce their own light. Bioluminescence replaces sunlight as the principal visible signal. It can conceal a silhouette, attract prey, identify a mate, warn an attacker, or create a brief distraction in the darkness. Marine snow continues falling from above. Dead plankton, fecal pellets, mucus, shells, and fragments of tissue connect the deep ocean to the life of the surface. At hydrothermal vents, however, another source of energy appears. Black smokers release hot, mineral-rich fluid, while chemosynthetic bacteria and archaea use chemical reactions to build organic matter. Giant tube worms, mussels, shrimp, crabs, and other animals depend on these microorganisms. Their discovery demonstrated that complex ecosystems can be supported by chemical energy rather than direct sunlight. Modern vent communities are confirmed. the idea that life itself began around ancient alkaline hydrothermal vents remains an unresolved hypothesis. Across the abyssal plain, life becomes widely scattered. Most animals survive on small drifting particles, while a whale fall can create a temporary island of abundance that supports scavengers, microbes, and bone-eating Osedax worms for years or decades. Finally, the seafloor bends into the trenches of the Hadal zone. At Challenger Deep, pressure approaches roughly 1,100 atmospheres. Yet amphipods, sea cucumbers, microbes, and other organisms continue to survive. Jacques Picard and Don Walsh first reached this depth aboard Trieste in 1960. James Cameron followed in 2012, while Victor Vescovo, Catherine Sullivan, and other explorers later descended in limiting factor. Even now, the ocean remains incompletely known. By April 2026, modern high-resolution surveys had mapped approximately 28.7% of the global seafloor. And mapping is not the same as exploration. A depth measurement does not reveal every animal, microorganism, chemical reaction, sediment layer, or geological process. The deep ocean is not an alien world separate from humanity. It shapes Earth's climate, oxygen cycle, carbon cycle, geology, biodiversity, and history. The bottom of the ocean is a real destination. Understanding everything that lives and happens there remains one of science's longest, deepest, and quietest journeys.